speaker now will be Vedran Dukov of Leiden on QML beyond kernels.
So we don't have what?
Don't like QRAMs.
I don't like QRAMs. No. We're going to mention them, QRAMs, in a second. So thank you very much, Konstantinos, for the introduction. And I'm sorry for the switch up of the talks. This talk is a little bit of an outlier. Well, there's quite a few outliers. This is a strange conference. QNLP and so many other things are discussed at the same time. So this is going to be very much quantum machine learning, right? Connected to classical machine learning to some extent. And it has to do with all this Nisky stuff, just to give you a heads up on what's coming. And maybe I do have a feeling that there are many experts in the audience. I might be repeating things that you might know, but I'm still going to go through the basics for those who don't have the background in machine learning in general. So bear with me. So I would like to just motivate the talk on why we're talking about quantum machine learning in general. And there's sort of two basic ideas, right? One, which is quite an old idea from the early 2000s, is that sometimes machine learning requires compute power. Sometimes you have to solve well, either a lot of computations or actually solve hard computations. For instance, you're thinking about 0-1 boosting, when you have to select a subset of classifiers, which when combined in the right way, solve your problem optimally. In which case we talk about the combinatorial optimization problem. And you know, this is hard, and there was an idea that maybe, you know, you can Grover speed up the thing, or maybe you can use an annealer and hopefully get better heuristics than you could do classically. This is like 2000 to 2006. And then around the time of HHL, Alessandra was talking quite a lot about it. It was noted that you can try to interpret quantum mechanics as linear algebra in a literal sense, like really as large matrix multiplications applied on a large vector, which may as well be your data vector. And then with an appropriate data access, you can hope for even super polynomial and exponential speedups. So process information in polylogarithmic time in the size of the data. So this was super exciting, right? But somewhere around the time where you and Tang came about and kind of showed that many of these things you can also do classically through stochastic processing rather than quantum, another important thing happened, which is that we had this first serious demonstration of a computation which is arguably beyond what classical computers can do, or at least is doing it in a very different way. And of course, I'm talking about the landmark paper of Google on quantum computational supremacy, which was this sampling problem which was done, which at the time was argued would require 10,000 years in a certain type of a quantum simulator. Not the best one, but one of them. Nowadays, we talk about 3 minutes for the same computation, but that's a matter of scale, right? This was on 53 qubits. If it was 60 qubits, the same arguments of 10,000 years would probably hold. Now, this was said to herald the NISQ era, the noisy intermediate scale quantum, where quantum computers are not fault tolerant. You cannot really do whatever sets of gates you want in whatever architecture you want to whatever depth you want. You're very limited in types of things you can do. And yet at the same time, you have first convincing arguments that it's doing something more powerful than, well, beyond what classical computers can do. And it's very frustrating that we've studied quantum algorithms for 30, maybe even close to 40 years, and then we spend billions, literally, and we get quantum computers that are completely different than the ones we would like to have, right? We don't know how to use them, and we don't know how to program them, yeah? So that's the frustration that we're all kind of feeling and then trying to get around. So the idea that came about from this picture is to somehow delegate the programming part to a classical device and to say, hey, Mr. Classical Computer, why don't you play around with the quantum computer and get it to do something useful for me, right? And this is what's going to touch upon machine learning, because machine learning is all about getting computers to do useful things without providing explicit programming, right? That's what we do. And this is the third flavor of quantum-enhanced machine learning that I'll be talking about today, where we're not trying to speed up a classically specified algorithm. We don't really understand the input-output relation we're going to get, but we're hoping that it's interesting and different than what we are accustomed to or can do classically. So it's about having really quantum-specified machine learning models. And the main player in all of these works, and they've been applied in machine learning, in combinatorial optimization, in certain types of variational quantum chemistry, condensed matter physics, PD, solving, you name it, people have done it, is the parameterized quantum circuit. right? So it's a quantum circuit which has gates like any other. Perhaps their architecture is predefined. Perhaps they're of constant depth, and maybe I don't worry about how deep it is. But each one of them, in principle, carries a free parameter that I can tune. So we're not talking about an alphabet from a discrete set. We're talking about a continuous alphabet of gates that I can apply. For the physicists, this would be sort of the duration of the pulse of your field that you apply that drives your evolution. So I fix this thing. Some of them are, let's say, completely free. They're the things that I will tune in my training. Some of them are going to be input dependent. So I'm going to set my gates depending on what my input is. I will measure some observable, which may or may not depend on the input. That's a separate topic. And the expectation value of the state that this circuit prepares, starting from some fiducial state, relative to a fixed observable, will be the output of my computation. So this is a function, right? It's a function which comes from a family specified by these thetas, which are these free parameters, takes x an input and produces an output, which, given by the Born rule, is exactly this. Is the trace of the observable times the state. Yeah? So the input is some set of tunable parameters. The trainable thing is other tunable parameters of my circuit. And the output is typically the expectation value with respect to some observable. That's the things you see most commonly in literature. And arguably, it's sort of the only thing you can have. You can kind of show that this is universal in many different ways, but I will not be worried about that. What I will think about this, I will realize that this is actually a hypothesis family. So now I'm switching my language to machine learning. I'm going to say there's a family of possible functions that I care about. They're my hypothesis family. And if I'm doing machine learning, I will be looking for one which does the job right. You know, what the job is, it might be classification, like cats v dogs, or it could be the right policy if I'm doing reinforcement learning or something similar. So I'm pretty sure that probably most of you know this quite well. So just to get the language down, so I will be mostly worried about supervised learning, like classification. So I give you labeled data, you analyze it, and then you try to understand what is the labeling function, what is the underlying law which assigns labels to data points, with the objective of being able to label things which were not in my data set before, so new points. I will be typically doing this by minimizing some of the training error. I'll be looking at how my model performs on the training data. And perhaps I will also add something which is called a regularization term, which is going to prevent overfitting, right? Because again, I don't care about getting the data that I know correctly. I care about getting the data that I don't know how to label correctly. So this is the error that I do on my data set is going to be called training error or empirical risk. And of course, ultimately care about the total error. There's a hypothetical quantity that I cannot really compute because I don't have access to all possible data points. That is what error would I have if I were to evaluate it on average on the entire space of things that I could possibly have. And the thing that I care about the most is so-called generalization performance, roughly defined as the gap between the training error and the total error, right? So if I evaluate my model on my training set, I get some quality of performance. What can I say about what it will do beyond my training set? This is a scaling thing. It's not a number, it's a scaling thing. You're trying to get this thing down, and it has to do with how expressive your model is. And you can do theory, characterizing just how large this gap can be. But of course, in practice, the results might be completely decoupled from theory, which is why well, we see deep neural networks work, whereas most theory tends to tell you that they shouldn't, that they should really, really catastrophically overfit. And we're still trying to understand that phenomenon. So there's this disconnect between theory and application. And this is sort of what we do in this field of quantum machine learning, for better or for worse. We look at some machine learning application. We find where the neural network is, or whatever the machine learning model is, kick it out, put in a quantum neural network, or this parameterized quantum circuit, and kind of hope for the best, right? That's simply the honest truth of what we do. And then now, of course, as scientists, you should all object, and you should say, that's not a good enough motivation, right? Tell me why on earth we should do such a thing, right? And the fact is there are deep reasons, right? Number one, let's say pragmatically, is because over time we've learned that models matter, right? The choice of the machine learning model makes all the difference. Again, the key example being deep neural networks, where theory said they shouldn't work until people tried. Data got large. It turns out in the size of the world we're in, they seem to be unbeatable, right? They're the best thing that we have. Whereas a single hidden layer neural network would not do the job just as well. It's a different machine learning model. And further, we have reasons to believe that these quantum models are not entirely uninteresting, as I'll highlight in a second. So two classes of questions that we typically ask. One is, can we get it to work? Can we train them? Do they match the device that we actually can build, and so on? Very pragmatic questions. What happens in the noise? Second kind of question, should we get it to work? Do they do anything interesting? What kind of types of these models are there? Are they all the same? Are they different types? Do they perform well? So this is the kind of thing that I want to talk about today. Not the first type of question, but the second type of question. And it just so happens that there are many types that we've studied so far. And roughly, they fit into one of these three camps. Not all of it. There are things which are, of course, outside of this domain in some sense. But these are the three types I want to talk about. So the first one is maybe historically the first one, which is the so-called explicit model. I will motivate why I call it explicit in a second. But it's characterized by the fact that the circuit is split temporally into two parts. The first part of the quantum circuit, which just depends on the data and is not trainable otherwise. And the second part of the circuit, which doesn't depend on the data and is trainable. So there's a clear separation. Quantum mechanically, things don't commute, so if I reshuffle things around, intertwine them, I get something different than this model here. I get something which we call a data reuploading model, where the data can be appearing in the circuit after certain trainable parameters and it doesn't commute through at the beginning. And then in the middle, we have something which is called the implicit model or the quantum kernel model, which somehow doesn't have this trainable part in the quantum circuit. It does everything quantumly, which just depends on the data, and then there's some classical information processing. And these two things, the explicit model and the implicit model, are intimately related. Right? So let me briefly reflect on this. For those who come from a classical background, who know about support vector machines, the difference between these two things is essentially whether you're thinking about SVMs being optimized in the primal picture or in the dual picture. That's one way of thinking about it, even though it all generalizes beyond to what we call kernel methods. So what we're really doing is a linear classification. So the way we're going to label data is going to be by finding a hyperplane in some embedding space. And this hyperplane is going to be a thing that we have to figure out in our training process. And once we do, everything which is in one half space is going to have a +1 label. Everything which is in the other is going to have a -1 label. What makes this very powerful is if we combine the idea of linear classification with the notion of a feature space. That is, we don't necessarily expect that the data without any pre-processing allows such a classification. But if we map it non-linearly into a higher dimensional space, then it just might become linearly separable. In fact, there's a theorem showing that you can construct maps which will always make any data set linearly separable, this covers theorem, even though that's not necessarily what you really want to do. So we have linear classification in feature spaces, two very important concepts. Just one thing to highlight again, the feature map, the thing which maps my data from the original space into this higher dimensional thing, that's not trainable. That I fix before thinking about the data set that I want to analyze. Now this thing here, this picture lends itself very naturally to a quantum processing thing, because I will simply take the natural Hilbert space of the quantum computer to be my feature space. So I will parameterize my circuit, it prepares some quantum state, it lives in an exponentially dimensional Hilbert space, which is sounding very, very appealing. And in fact, this other part of the circuit that I do turns out to implement a normal of a hyperplane in this high dimensional space. It is not the space of rays, of kets, of vectors. It is the space of density operators, or more specifically, it's the space of Hermitian operators. So my feature space is a 4 to the n dimensional real vector space, not the 2 to the n dimensional complex vector space. And this thing here, which you recognize as the Born rule, is nothing but an inner product, right? So it's an inner product between this vector and this vector, where this is the data, and this is the normal hyperplane, the normal vector specifying the hyperplane. Don't be confused, it's an observable, but it's a matrix. Matrices are also capable of forming vector spaces, right? They can also be vectors. The critical thing, however, is that when I think about the quantum processing thing, the types of normal vectors that I can express here are not all of them. I'm constrained by my choice of the observable, which in particular fixes the spectrum that I can have. And second, the eigenvectors that I can get of the observable depends on the variational part. If this is not an infinitely expressive circuit, an arbitrary unitary, I'm only tapping into a part of the space that I can actually select my hyperplane from. And this turns out to matter, right? If I ignore this part here, then it's just a universal, whatever hyperplane you want in this exponential dimensional hyperplane. And once we understand that there's this encoding part, and then there's a part that I'm looking for a hyperplane, we have to find the optimal hyperplane. There's a primal optimization problem for this. If you look at its dual, it turns out that you can express everything that you want, not in terms of vectors in this higher dimensional space, but in terms of inner products of vectors in this higher dimensional space. So you don't ever have to actually write down the large vector as long as you can evaluate effective inner products. That's the basic idea behind kernel methods, which avoid going to these exponential high dimensional things. It has many consequences. One of them that you don't have to train the quantum device. You can just evaluate inner products, put it in a classical computer, and evaluate things further on. There's a lot of mathematics suggesting that it's the only way that we should be thinking about it, in the sense that we know that in some sense optimal classifiers can always be expressed in this fashion when I just think about the inner products and not the mapped space. I can completely avoid thinking about these explicit models. That's assuming that I don't care about the fact that I cannot really reach all the hyperplanes in the explicit picture. Right? If I forget about this fact, if I pretend that this is an arbitrary complex circuit, then indeed I should probably be thinking about kernels and not explicit models. Now, kernels are very powerful. They're a powerful tool to understand what this type of machine learning does. They also perform really, really well. There's a lot of work in this area. So how bad would it be if this is all there is in the quantum case, if we never have to think about explicit models? And it turns out that, well, it's not very good, in fact. There's a wonderful paper by the Google team called The Power of Data or something or other, where they kind of produce a type of heuristic which tells you whether a data set is going to be better treated by a quantum model or a very simple classical model, where the quantum models are restricted to these kernels. And it turns out that there's this very narrow margin where you can hope for an advantage from a quantum device. So it kind of looks very, well, we would have hoped for more, right? The upside is that there's going to be sort of the main message of one half of the talk is that there is more than that. It's a little bit of an oversimplification, saying it's just kernels and there's nothing else. So this is what we started thinking about. Well, is it really the case that we should only be thinking about the implicit model? Does it matter that these hyperplanes here are not arbitrary? And what can we do about these data reuploading models, which are not expressible as either of the two because of the non-commutativity properties? And now this brings me to the three results that I want to share with you. I will not spend too much time on them. I will refer you to the paper, just the main findings. Number one, these more general models, data reuploading models, can be faithfully mapped onto explicit models. So you give me whatever data reuploading model you wish. I can explicitly, efficiently construct an explicit model which has some part of the circuit which depends on data only, followed by part of the circuit which is data independent and otherwise tunable. And it will be a specific circuit. It will have a certain architecture. And it's if you know essentially very basic things from quantum computing, it's not surprising. It's essentially using gate teleportation to commute things through where you shouldn't be able to do it at the expense of introducing post-selection, which it turns out doesn't really hurt us in the type of analysis we care about. So these data reuploading models, which are at the face of it strictly more general than the explicit linear models, are not. They turn out to be the same thing, right? But again, it's critical to understand that it is important that we don't get all hyperplanes, that some are inaccessible. If I allow all hyperplanes, I get nonsensical models. And that's in fact the second finding. We show that you can look at these results of Google where they've demonstrated these classical machine learning models perform just as well as the quantum ones, if not better. That's the case if you move to kernels, because kernels sometimes dramatically overfit. And if we stick with the basic explicit picture, this doesn't happen. And then these plots, which again I cannot discuss too much, so these are comparing what the quantum and the classical kernel would do. This is sort of a measure of error in the validation case, so error on the total error, so to say. And this is the full quantum model. So on the same type of experiments that they did, we do the same thing, just don't ignore the fact that you should be dealing with a restricted circuit, and we get much better performance. So message here is not everything is a kernel. Sometimes if you want to have advantages, you really have to stick with the explicit model. And finally, even though we first proved that explicit models are contained in data reuploading models and the other way around, which is the surprising part, there are fine-grained differences between the three. So we construct a machine learning problem in a packed learning setting, probably approximately correct learning, which you can sample efficiently learn using just one single qubit in a data re-uploaded picture. So give me a single qubit, and there's going to be a bunch of gates. Some of them depend on the data, some are trainable, and you can train it in such a way that with logarithmically many samples in the dimension of the data, it gets perfect performance. If you want to do the same thing with an explicit model, so that's the one where I first have to do the data input, then I get to process it, you need linearly many qubits in the dimension of the system. And you cannot do it without. If you have less than big omega d, it is going to catastrophically fail. And if you want to do it implicitly, meaning using a kernel, then you need to have exponentially many samples. So in fact, these two guys, the data reupload and the explicit one, they're efficient with logarithmically many samples in the dimension. The kernel needs exponentially many in the dimension. So it's a doubly exponential separation between the settings. And the consequence of this is you cannot simply forget about all three. It is not the case that we can stick with explicit models and that's all we care about. It's not the case that we just should use data reuploading models or just kernels. You kind of have to know what you're doing, which for those who are familiar with no free lunch theorems should not be very surprising, right? For some problems, you have to pick the right tool, and there is no such thing as a fully universal tool. So that's sort of my summary for halfway. From a very theoretical point of view, our main finding is for a broad class of quantum machine learning models built around parameterized circuits, there's one paradigm that captures everything, and that's the paradigm of explicit circuits, where your data comes first, followed by fully variational part. But do not forget the fact that the variational part is still constrained. You cannot implement arbitrary unitaries, you can only implement a certain set of unitaries, and that's very, very important. If you generalize, you get nonsensical overfitting models which are useless for any application. On the other hand, we've also done this fine-grained analysis, looking at the resources, resource counting, learning efficiency, and so on, only to find that not one rules all. It is not the case the explicit model is going to be better than a data reuploading model. In fact, for every case that we've really studied, you really should be using a data reuploading model. It is simply better behaved. It is more efficient in terms of sample complexity. It is certainly more efficient in terms of the number of qubits you need to use to get the same kind of performance. But it might be more difficult to train. For instance, many of you are familiar with Verne plateaus. They behave slightly differently in the two pictures. So again, not obvious what one should do. It is all situation specific, right? And this is going to be kind of my main message here, is that in machine learning, things are always more complicated than you like them to be, and that theory only gets you so far, and that the proof is in the pudding, and that you really have to apply your thing to a particular problem before you know whether it's any good at all. And that's why, you know, claiming victory or loss for quantum machine learning at this point right now, I personally feel it's a little bit too early to make a call in either direction. So our main challenges are that we need, you know, more theory, of course. Nothing is more practical than practical theory. But we need tests, right? We need to run these things somehow, and this brings me to the second part of the talk, because of course we cannot run these things, right? We need real experiments on real devices, on real data, and that's just too difficult. Why is it too difficult? Because, I mean, come on, we're inventing machines which cost literally billions, exploit, you know, the most exotic theories we've invented in the last 2,000 years. Please do not apply it to MNIST, right? Don't classify something that you can classify with a single hidden neuron thing. Please don't upload, because I will do exactly that. I will apply it to MNIST, and I will be very apologetic about it, but I will at least admit my hypocrisy at this particular point. So somehow the expectation is, if these quantum models that are so super complex, if they make sense, they probably make sense in something which is super complex by itself, right? Not in the easiest task, but in the more complicated ones. Maybe high dimensional, maybe very complex, convoluted, and so on. But we cannot access experiments there, because we have only very few qubits which we can actually train, and even fewer that we can actually simulate, right? So somehow, what do? So the idea that we had is, as you'll see, it's inspired by this idea that you can somehow use a smaller quantum computer to simulate a large one, but I will drop the idea simulate. I will ask, you give me a smaller quantum computer and classical processing, can I mimic in some not fully formal way what a larger quantum computer would be able to do? That's my question. This is our starting point. I call it the circuit shop. It's a result which is well known and studied by many. I think the very first ones were by Bravi and his collaborators in 2016 on trading off classical and quantum resources. So what's the idea? The idea is that, if you take a 2-qubit gate, you can always write it down as a sum of at most 4 products of single qubit gates up to local unitaries. So this thing here, this sum does not have a physical meaning, right? I cannot implement sums of unitaries. I can multiply them by applying things sequentially, but I cannot sum them up. But mathematics allows me to do it, right? And in fact, the number of gates I'm going to get here for single qubit, 2-qubit unitaries, well, one of 3 things. It's either a product unitary, or it's Schmidt rank 2, or it's Schmidt rank 4. These are the only 3 options that are possible. So no more than 4. And in fact, if it's a CNOT gate, which is very commonly used, then 2 suffice. I will have a sum of 2 things, single qubit unitary here, twice. I'm going to add them up with a given prefactor that you can explicitly compute. So that means that I can take my original circuit, I can draw an imaginary line separating into the top part and bottom part, and then this line is either going to cut some entangling gate along the way or it won't. Like if it won't, I'm very happy because in fact I have 2 circuits that I can treat separately, evaluate separately, and then simply multiply the expectation values to get the expectation value of the entire thing. Or maybe I will cut a CNOT here or there. In the moment that I cut it, I can simply express this as a sum of 2 circuits, which have 2 different unitaries acting in the place where the CNOT was. Yeah? We'll have a sum of 2 things. But these 2 things that I'm summing over are now again product, right? So I can evaluate first element of the sum, second element of the sum on this half-sized quantum computer, add them up, voila, I have the outcome that I want. Now, the problem, of course, is that I'm going to typically be cutting more than 1 CNOT. And the number of things that I have to sum over grows exponentially in the number of CNOTs. And in the general case, I think this is continuously being improved. I don't want to lie to you. I think the best result a few weeks ago was like 9 to the power of cuts. I think now it's like 4, but I'm not sure. If you ask me, I'll find the references for the most efficient ways of doing it, right? So the thing is, yeah, you can do this. You can cut up your circuit to fit your device. You can do more than 1 cut, of course. It generalizes. But the number of circuits you will have to run grows highly exponential in the number of CNOTs you cut, and the number of CNOTs you cut have to do with how entangled your circuit is and how much it's actually tapping in the quantum effects, right? So it's not a practical thing. You will never be able to run these things, and don't get me started on errors, and God forbid there's a constant error, your thing, and everything goes away, right? Nothing works. But I can ask the simple question, but what happens if I don't really use all the terms? Do I really need all of them? Like maybe there's exponentially many terms, but most of them come in with very small weight. Maybe I can ignore them. Maybe there's small errors, right? Maybe there's some concentration effect saying that, well, actually a random sample does just as well. This we don't know. We don't know whether things concentrate. This is related to the sign problem issues for those from more at home in quantum simulation. It is not very likely that I can just randomly choose a subset and be happy with that. But there's a chance that maybe choosing a certain subset, but I don't know which, will be a good proxy for what the full circuit would do in some cases. I'm in the world of heuristics, I do machine learning, I'm allowed to say in some cases. I'm not looking for universal proofs. But even if you give me this, even if you believe me that selecting maybe a polynomially small subset of an otherwise exponential large sum is good enough, I still have to kind of decide which subset. And that's a problem, right? Because now I would have to select a good one, and this is explicitly a combinatorial optimization problem, right? I have to select something out of an exponential large set that's, exponential choose polynomial. That's my search space that I'm dealing with. So you can forget about it. This is never going to work, selecting a subset. The funny thing is that I don't really have to do that. So there's a lot of text here. I'm going to try to, please don't look at the text, but I still have to speak here. Don't look at the text, look at me. So I have this circuit which was cut, recall, right? I cut in half, and I had a CNOT here, And because I had a CNOT, suddenly the world duplicates into two copies, one where I have some two single qubit gates appearing here, and then another one where I have another pair of two qubit gates appearing here, okay? No longer entangled gates, just two qubit gates, but they're different, and that's why I have to treat them differently. But these two circuits now differ just in those two places, nowhere else. All other gates are the same. So I'm going to generalize the circuit instead of having this fixed gate here, which comes from the decomposition of a CNOT, and make it parameterized. So now for some setting of the parameters, my circuit looks like the left-hand side version, or for you, the right-hand side version. And for other setting of parameters, it looks like the right-hand side version. I've added parameters, but now I have the capacity to represent both. You can do this for every single CNOT you cut. So I can predefine how many terms I want. I know exactly which gates are going to appear because of cutting of CNOTs, and I make them parameterized. So I add parameters to the circuit where there were none. So I'm generalizing the model in that sense. But I'm going to keep only very few terms in the sum. That makes the model weaker. And now, as I'm training the model, since these parameters are free and they can start looking like whatever model I want, the training itself is going to select the subset that I actually want to do. So technically speaking, this is a relaxation of the combinatorial optimization problem that I had before, where as a hyperparameter, I choose the number of terms I want to keep. So what can I immediately say? Well, I can immediately say that no matter what performance I would have gotten, at least with respect to the training part, to the empirical risk, in the full model, in the case that I kept the optimal subset of terms, I can recover the same performance in this model, which has these additional parameters. And because I'm adding parameters, it turns out that the optimization actually becomes easier. Well, it's kind of obvious because I moved from combinatorial to the relaxed version, right, to the continuous relaxed version. So I have a very complex model. I drop a bunch of terms but make it more general. It's not entirely clear what I did to the model, but suddenly I can train it. I can run it on a smaller device. And this is what I mean by mimic, right? It's not the original model that I started from. It is inspired by the original model, under the assumption that exponential sum is not really fully meaningful, that I only need a part of it. It is going to be equally well-performing as the original quantum model. That's the hope. The thing that also happened along the way, by adding these parameters, I'm no longer looking like a quantum circuit. So the types of functions that I have here, which have this parameter zeta appearing here and these lambdas here, they no longer correspond to a larger quantum circuit that was cut up. It's a truly hybrid thing without a quantum analog. If I want to have a quantum circuit which does this, it would become impractically large, right? So it's something different. It's a hybrid thing. But I can still analyze it. So one of the things that I can analyze, I can study is generalization performance, which, by the way, is not a trivial thing because, again, let me remind you, I start with a large quantum circuit, then I cut it up, and I have something which has exponentially many terms in the sum, but this is exactly the same hypothesis family. Then I drop a bunch of terms, so I'm simplifying the model, but I make the terms more general. At the face of it, it's not clear what this did to the model. But if you take any of the standard approaches to bounding the generalization gaps of quantum machine learning models via pseudo-dimension, via the generalized trigonometric polynomials, covering numbers, certain results that we did which have to do with fat-sharing dimensions, it turns out that they're all of them are completely blind to these internal steps. They do not see a difference between this final picture and the initial picture, which is kind of the most boring and problematic result, but also not a bad result. It means that what we got is not worse than what we would have had if we used a full-blown large quantum computer. It is not worse than that. On the other hand, we kind of were hoping that it's maybe better because, maybe this is much simpler than what we had. And in fact, you can do that. You can improve on the bounds that people have studied before by taking into account that these models are smaller, that they're product, that they're sums of products, using certain results involving so-called Minkowski sums, which take unions of hypothesis functions. This is something still under study, but for now, all I can claim is that it's not worse than the model we started from, with respect to any measure that people have studied in the literature who are not us. We can do slightly better than that. Cannot give you quantitative statements for this. We're still working on it. But it's not I would say not an uninteresting thing to do because this thing we can run, right? In fact, we can run models which have 600, 700 qubits and get non-trivial results out of this. Second thing, for those who worry about the training aspects, the Barron plateaus, this is a very particular mathematical structure. It's an additive multiplicative model. That's what they call it in the optimization community. And because I know it looks like this, I can come up with optimizers which are kind of aware where the Barron plateaus would come and not get stuck where the full-blown quantum circuit would have gotten stuck. So it's never going to be better than the power to train just a single small sub-circuit. Like if that one is impossible to train, then the entire thing is impossible as well. But it can be that the original circuit, the large one, was impossible to train, but the cut-up one that we have is not. That the optimizer now suddenly works. So that's kind of an interesting thing. And of course, it gives you a systematic way of hybridizing further, right? Because right now, still everything is a circuit, but there's no purity police which is going to arrest me if I put one term to be a neural network. I'm allowed to do that. I'm allowed to do other crazy things like compose this with certain wavelet functions and get things which don't have, let's say, Fourier support over the entire space, but maybe it's localized. And we know that it's very important. That's one of the reasons why wavelets are very successful in machine learning, because they're really localized. So you can do that in this picture. We haven't done it, but it can be done. And then we tested on MNIST. And here, I apologize profusely. We did the first thing we could because honestly, well, it's difficult to find a very good data set, but this is a sanity check, right? Can we do the basic thing? Yes, we can. It learns the basic thing, and it does so without dimensionality reduction. So it's simulating a quantum machine learning model over 64 qubits that we don't have. It does it on a laptop. We also try to train models which come from a large circuit. Now, in this case, it's no longer 64 qubits that we're simulating. I think it was something like 20 qubits, but then we chopped it up. And we see a nice cascade. The fewer terms we keep, the worse performance. So this is error. This bottom line keeps 40 terms. The top line keeps only one term. And we get the kind of performance that we would expect. Like if your model is quantum, then you need to keep a lot of terms. If your model is not quantum, MNIST, then in fact the number of terms you kept was essentially irrelevant for performance. This is not a mathematical statement. I'm not claiming this to be true. I'm just observing what we saw in plots. I'm not categorically claiming anything. It's not a theorem. Just an observation which I hope, well, motivates me to do further research here and maybe might motivate others as well to think about hybrid models. So yeah, so I think I've already given the main take-home message that I want to give before. If you want to do quantum machine learning, don't forget about your data and don't forget about no free lunch theorems. It's going to work for something and it's going to fail for something else, which is not an excuse to not do theory. Right? We should still do theory. It's going to guide us moving forward. And with this, I would just like to thank my entire team who worked on this. And everything that I discussed is already implemented in TensorFlow Quantum. If you want to play around with it, it's easy to download. And there's a small tutorial that we've done there. And I thank you for your attention. Ross, you're going to have to scream, apparently.
Or maybe. So this divide and quantum approach you described, could you say how it compares to the cut-QC of multi-modulation? It's a similar kind of idea.
So I'm not entirely sure what, I don't know what cut-QC exactly does, but I would expect that it does the verbatim cutting of the circuits, and then not much more than that. I mean, the defining property of what we do is that we no longer try to mimic the full circuit. We give up on it and accept that it's going to be very different in some cases and hope that it's going to be similar in others. So we're not mimicking the big circuit. Don't use it for quantum chemistry, right? But maybe for quantum machine learning.
Other questions? I have a question. Every time you cut, can you optimize the circuits to reduce the CMOS?
To reduce? Yeah, sure. You can do it all along the way. No.
If you do it, the prefab, the exponent will change.
Yeah.
And like how many terms you get.
Yeah. No, certainly. I mean, all these smart things can be done on top of it, for sure. For us, it was more about not how difficult is it to execute one sub-circuit, but whether we need them. Right? That's the main question. Sorry. So in short, yes, you can apply optimization to every sub-circuit, but for us, the question was not whether you can implement those circuits more efficient, but whether you need them at all, or whether you can drop most of them. Maybe quantum is not that quantum for machine learning.
About what are you going to talk about?
Sorry, change the title.
Change the title.
I'll explain.
Okay. Take it away.
Yeah, okay. Okay, so I've recently got a project funded in collaboration with CQ and the BBC, Continuum and the BBC. And obviously, I'm from UCL, so I thought maybe it's better if I talk about anaphora and ellipsis resolution using quantum methods in the context of the bigger picture of our project. And so, I've listed all the students who've helped me, and hopefully Shashwat will also start next year. And most of them are here actually in the room. And their names will come up later as well. And so this is a 5-year senior research fellowship by Royal Academy of Engineering. Sorry, a lot of propaganda. Okay, so I would like to sort of promote this project the same way as I did it to them. So, so the idea is that we live at the age of data. There is a lot of data around. There's good data. For example, the data that is collected by nurses daily, which apparently gets accumulated and nobody uses it. So there are, I would not have thought of this, but there are collaborations between nurses and mathematicians, how to take advantage of this data automatically, properly. And there's obviously bad news, fake news. And there's also a lot of ugly news, obviously, around, the news we don't really want to know about. And a lot of initiatives to take advantage of the data, like on the umbrella of that mathematicians and nurses collaboration, there is this new initiative by the NHS, Data Saves Lives. Okay, so why is that related to us? I'll try to motivate. So we send 100 million text messages every minute. A third of our waking hours is spent streaming, average person. And we receive about 30 to 40 gigs of data every year. So obviously, we get overloaded by this data. And the data is obviously not managed properly. Everybody uses one way of streaming to spend time at home. And I'll show like one sample problem. So an example is very recent, hopefully past pandemic. And I want to know more about it. So imagine I came from a country when there was no COVID-19, or even in the UK, I want to sort of know more about COVID-19. Is it related to any other past pandemics? How do I have to deal with it? But if I enter COVID-19 in the search option of iPlayer, I get unrelated data. It's really astonishing. Then let's try Netflix. Maybe they have more money, better budgeted. If I put COVID-19 in the search item of Netflix, I also get unrelated content. Let's see. Hopefully, I will survive. And in fact, my Netflix feed is full of unrelated content. It's like, OK, my daughter uses my account, obviously. And you just see popular on Netflix. That's the first one, is just things that are popular, things that everybody likes. These are the things that may become popular. And these are the things that we watched in the past. So this relatedness of data doesn't come up at all. So, OK, so the idea behind this project was that the simplest type of this data is text. And in fact, when I was working with the BBC, I became aware that they have huge archives of media. Imagine all the programs that BBC ever produced on radio and television over these years. They actually have a record of it, and there's this physical archives. I was given a tour at some point. And most of it can be represented by text. So each of these TV and radio programs, they've got title, description, they've got synopsis, they've got script, and these days you can just run speech to text and get subtitles for them. And so why advances in natural language processing haven't been taken into account when searching these archives of data? So the search option of Google works really well. If I put COVID-19, it tries to sort of guess what do I want to know about COVID-19. So search works really well here. And if I say, like, what do I say? I even get what I wanted to find out when I went to iPlayer and Netflix. I really wanted related footage about COVID-19, which I did not get there, but I do get when I just search for COVID-19 in Google. Due thanks to advances in NLP that Google knows about and other programs do not know. So that's the idea. So we want to develop mathematical models to represent semantics of this textual data and code it in a software package, and then use it to relate data. The specific test case of this project is to generate media recommendations. You have to give ideas about things you want to watch in the future, which are related to the things that you watched in the past. And obviously, it goes very easily and immediately beyond media recommendations to any area that has text-heavy products, right? OK. So I want to show how improvement in this area is immediately extremely possible. Okay. Take it. Okay. So just by arranging the text that comes from the subtitles of the programs in a very slightly structured way. So the title of the project was, if you remember, was like Engineering Mathematics for Modeling Typed Text Structures. Actually, I wanted that acronym to be Amethyst, so that's why I came up with that title. It's the second name of my daughter. So if you structure this text, instead of in vectors, in matrices. If you want to ask me later, I'll explain how do we put the text in matrices. Very simple procedure. So instead of just having a flat vector, you just arrange it in matrix, and then run some kind of matrix similarity. That's important. What kind of similarity? What kind of operational matrices you want to run to get a nice notion of similarity. Then you immediately get a lift in the accuracy of, for example, BBC's recommender system, which we worked with. So I'll quickly give a run through. So we worked with 2 data sets. One was like a weekly data set of 146 programs. Then later, we also got access to a monthly data set of 900 programs. So think about calculating program similarities between pairs of programs, right? So 146 times 146 divided by 2, and similarly for this 900, because you have to calculate similarities between every pair of programs in these data sets. And the idea is that, okay, you'll build not vector, obviously matrix representations for these programs, such that things like surviving COVID and SARS, the true story, will become close to each other, and things like Voice UK and EastEnders will be close to each other, and these will be somehow far away from each other in some plausible scenario. And these are our results. So in our model, the recommendations that you get in top, let's look at top 20. In top 20, the accuracy is 18%. It's a very low accuracy. But the baseline that the BBC had was only 12. So you see the raise of around 6% from 12 to 18, just by putting the subtotal files into matrix X. And if you don't put them in matrix X and just use doc2vec vectors, then you get 13.88. So look at the difference between. So from 12, you do get a raise to 13, but the story is very different if you go to matrices. Then, well, maybe this data set is too small, and this is just, these results aren't reliable. It was just chance. So we tested on the monthly data set, and although the accuracies are quite low on the monthly data set in general, baseline is 2.6. The normal doc2vec model gives 3.2, but our model lifts it to 4.14. If you want to know if these differences are statistically significant, they are very statistically significant because the data set is quite large, 900 times 900 divided by 2. Okay, so this is our target data set. Then here are some examples. So if you look at The Life of Rock by Brian Perrin, so this is a BBC program, what BBC normally recommends to you is anything that's of type comedy spoof. So you get these things. But if you look at the recommendations that our program produced, you get all this top of the pop-like programs, Story of 1979, Top of the Pops 2. You get Queens of Disco. You get Neil Sedaka, the King of Song. They're all very relevant. Do you agree? Do people agree this is relevant? There's also subjective relevance. Similarly, if you look at Wild China, these are what BBC recommends to you is all their nature and environment programs of the same genre. But if you look at what we come up with, you get like Animal Odd Couples, because Wild China is about wild animals in China, the Lost Kingdoms of South Africa, Russia on 4 wheels, etc., etc. So you're right. Okay. So now moving on. So we want to sort of like do a proper mathematical modeling of this kind of text. Obviously, we want both a logical representation of the data. So something like Lambert calculus for the grammatical structure within sentences. And then what we've been working with is actually not a new idea, but piggybacking on ideas that were present a lot in the communities add some kind of modalities to Lambda calculus to extend the expressive power, which would then enable you to move from sentence to kind of document structure, the structure, discourse structure that exists between sentences. So that's where anaphora and ellipsis comes in, any kind of co-reference structure. And to this, well, as you saw, we want to add statistical information. Normally, we would work with finite dimensional vector spaces, some kind of deep neural network embedding, doc2vec, any Baird family embedding. But thanks to CQ and Bob's efforts, we also now have access to methodology that would give us a different kind of statistical representation in the form of quantum circuits. So I'll start by giving some kind of technical background. So this is Lambeck calculus from 1958 paper of Lambeck, mathematics of sentence structure, sequence calculus format. These are the left and right implications, which come as residuations to your tensor product, which is non-commutative, highly non-commutative. On the left is just pretty printing for the comma of the sequence, the list comma. On the right, you have to be very clever and divide your context into two separate things, gamma 1 and gamma 2. From one of them, you get the first multiplicand, A, and from the other one, you have to take the second one. This is a very difficult rule in proof search. Now, what people have been doing for a long time, starting from Muriel and Mortgott, and later on Jager, work of my PhD student, Gijs Weinhold, and what Lachlan has been doing since 2021, I think, and our papers started from 2022. And when I was writing this, I didn't have space to add. CCG also has a model version, thanks to Jason Baldridge's work. I want to look at Steve. So that CCG also has a model version for very similar reasons. So the logic we ended up working with, so we changed perspectives quite a few times until we finally found the right logic. I'll explain why. Is something called Lambeck calculus with soft sub-exponentials, which is recent work of Max Kanovich and friends in ICHCAR 2020. So what they do is that you add modalities to the Lambeck calculus space. Nobody actually stops you from adding more modalities. These logics can easily become multimodal. But at the moment, we've got a bang operator and a nabla operator. Nabla makes you permute things on the left and on the right. So you can only permute types that you've marked with nablas. Bang is going to enable you have access to a banged type that is like a storage. So it's not like copying. We used to sort of work with copying things, which weren't the right approach. But this approach says you've got a storage, some kind of a limit object, where you have a lot of copies of something. And then you can get access to those copies by applying this left rule, and you lose your bang. So it's a one-off application of the rule. You have a bang of A, you get n copies of A. Again, then not for any n. This n is bound from upper limit by a k. So a Lambeck calculus with a soft sub-exponential comes with a bound k, and these n's are variables that move between 1, so there should be at least one copy, and that upper bound k of the logic. You can fix k to be 100 if you want. K and n can also be equal if you want. I'll say something about this later. And yeah, so this is like a projection operator. And the storage is something like a limit object in a category. It has all the copies in it. OK. So as usual, to get vector space semantics, we give an interpretation to the formulae and sequence of this logic. I think people are familiar what it's done to the tensor. So the tensor of formulae goes to the tensor of the vector spaces you assign to the atoms, finite dimensional vector spaces that you assign to the atoms of the logic. Nabla is identity, left and right multiplications are also done using tensor and the dual operation. And now what is the bang? It's some kind of Fock space, but because we have an upper bound in the logic, not any Fock space, a Fock space that is truncated from above by the bound of the logic. So here you've got, obviously these cases are different, that's the field. So you've got 1 copy, 2 copies, 3 copies, and all the way up to, okay, 0 copies for bound of logic, okay. So when in the previous slide, that rule is projection, and in fact, in reality, these are also the projections to the different layers of the Fock space. If you need A, you project to the first layer. If you need 2 copies of A, you go to the second layer, and so on and so forth. Okay, this logic has very good methodological properties, so it's decidable. All the logics we worked with before were undecidable. It doesn't have the cut rule, which makes proof search easy, but it has a theorem which says cuts are admissible. You need this for semantic reasons. If you need them, it has a strong normalization property. It's sound with regard to this finite dimensional vector space semantics that we work with. And we also came up with a string diagrammatic calculus for it. Now, with regards to text analysis, very easily then you can talk about 2 sentences that are connected to each other via an anaphoric relation, for example. If you say, Andy slept, he snored, then you want to bang nabla, the type of Andy, because you know that you have to move it so that it can get taken by the type of he, which is nabla n backslash n. He is something that either needs something nabla from before or after it, anaphora or cataphora. In this case, it's anaphora. You copy it. You not copy it, project it to the second layer, so you get 2 nabla n's. One is going to get cancelled with slept, the other one is going to get moved to where he is, and then get cancelled with he, provide the subject for snored. That's the general methodology. Similarly, for Andy snores, Nana does too. This is a case of ellipsis. This similar story. What you're projecting is your verb phrase here, so you bang nabla, the type of the verb phrase, snores and backward slash s, then project and move. We've worked with kind of complicated examples. So the moment you talk about anaphora and ellipsis, like many natural language phenomena, you'll face ambiguities. So here we've got structural ambiguities, like Philippa likes her dad, Ada does too. Who's that? If we're talking about A does that, then here's the proof tree. If we're talking about Philippa's dad, Philippa likes her dad, Ada also likes Philippa's dad, this is the proof tree. Luckily, everything is automated. We don't have to do this. We don't have an automation. Okay, you also have semantic ambiguities, which is the topic of this talk, really. For example, you have the dog broke the cat, it was clumsy, right? We as humans, because we have extra knowledge about the world, we know that it is referring to the dog. But if it was the dog broke the cat, it was fragile, then it obviously refers to the vase. But machines don't know this very easily. But we provide different proof trees for these 2 interpretations. Okay. Okay, so in the same way as you have different proof trees for these different interpretations, you also get different string diagrammatic semantics. So we start with the normal string diagrams, a vector space, the tensor of 2 spaces. Then we introduce a new notation, like thick line, for the Fock space. We worked for a while to sort of decompose this Fock space, because it's the direct sum of lots of tensors, but direct sum doesn't have nice diagrammatic notation. So we're just like, okay, for the moment, let's just put the thick line. In the same way as you have projection element of a vector space, you also have element of a Fock space in a very similar way. And the linear maps that you had for vector spaces, they also hold all of them for Fock spaces. In particular, we have a projection map, a special linear map. For Fock spaces, which is a projection, a thick line goes in, and then you can get access to whichever layer, nth layer of the Fock space. Now, a common operation that we will do in all of our examples is that you do the morphism that gives you access to an element of a Fock space. So this is an element of a Fock space, and then you project from it, right? So this is a very common operation. Again, we've got all the other maps, and here's an example. So we've got the dog broke the vase. It was clumsy. How you proceed? So this is the diagram of the proof tree. You have the element of the Fock space, the dog. Remember, you bang upload the dog. There was a bang by the type of the dog. Then you project to the second layer, because you only need 2 copies in this example. You can't swap in vector spaces, so lines cross. Then you give 1 copy of the dog to Brooke, the other one to it. And you got a nice diagram. And that's the diagram for the other interpretation. The dog broke the glass. It was fragile. OK, so what about quantum circuits? So we sort of use all the CQ toolkit. So we've got quantum circuits exactly the same as them. So that's like for a word which has no tensors in it, just a vector space. If you have a tensor of 2 vector spaces, this is your quantum circuit, similarly for 3 and 4. But unfortunately, as people probably are thinking, there is no quantum circuit counterpart for Fock spaces. Now, I was so happy when I came across this paper in Quantum Information branch of Nature. People are trying to sort of have quantum circuit counterparts of Fock spaces, so maybe we can use this later. But for a time being, we remedied this problem by noticing what I was saying before, that the only operation we do with Fock spaces in the examples we've considered so far is that you go to an element of a Fock space and you project from it. And this operation can soundly be modeled just by a tensor of the projection layer you projected to. So here, if P is 3, you can use this, the rank 2 tensor. So we shorthand, if you want this, to such a trapezoid with n legs emanating from it. And obviously, that has a corresponding quantum circuit. So then now we can draw quantum circuits for different interpretations of these sentences. This is for one version, this is for the other version, and now I'll show the results of some experiments. So we want to use these circuits, obviously, and so resolve the anaphora, resolve the ambiguity that's present in the anaphora by doing some learning on the quantum computers rather than classically. So there are many different data sets available for these pronoun resolution cases. So we work with the one introduced by Rahman and NG in QNLP 2012, which is a case of the Vinograd schema challenge. I'll say something about this a bit later. But as people, so that data set has 941 sentences. Our data set only has 144. And we work with a very small subset of theirs. So the sentences are of the following form. The fish ate the worm, it was hungry. The girls ate the cookies, they were starving. Man U lost to Liverpool. They didn't play well. So these sentences should all cluster in the same part of the vector space, had we a vector space. And then the other sentences, Man U lost to Liverpool, they played well. The girls ate the cookies, they were delicious. The fish ate the worm, it was tasty, should cluster on the other side of the vector space. So this is the classification task. Sentences where the pronoun of the second sentence refers to the subject of the first sentence, and the sentences where the pronoun of the second sentence refers to the object of the first sentence. So we run this as a classification task, and here are the results. When we work with these diagrams, because we have two sentences and there's two lines coming out of the diagram. Similarly, there'll be two lines coming out of the quantum circuit. And for classification, ideally, you need just one number, right? One probability distribution. So we had to think about how to join these two lines together. Obviously, one natural option in quantum circuits is the spider, so we join them with the spider. Another option was you just join them with a box, and you learn the parameters of that box to be learned by the quantum circuit. And it was really nice to see some differences between the accuracies. So what we learned, I don't know, we may be very wrong, is that if you run these models for long enough, your error function will converge, and your accuracy will go high. Is that true? Is that true? So, but if you then run the quantum model that we joined, the sentences with the spider, with the same parameters as with this box whose parameters we learned, with the same sort of values for the same amount of time, the convergence of the spider was much quicker, much higher accuracy, somewhere close to 100%, between 90 and 100. But with the box, it became much lower, so around 80% accuracy, and the convergence is also not as low as the other case. So that's something we learned from this. And finally, our goal in this part of the project is to attack the Vinograd schema challenge, which was suggested by Hector Levesque in 2011 as a rival to the Turing test. So he argued, if you want to delineate humans from computers, this is a much better test than Turing test. So let's have a look at the first sentence. Police denied demonstrators permit since they feared violence. Who feared violence? The police. Police denied demonstrators permit since they advocated violence. Here, the demonstrators advocated violence. Humans can solve all these references. Machines cannot, because they don't have access to world knowledge and common sense reasoning. So our goal is to try to solve the Vinograd schema challenge with high accuracy on the quantum computer. And then I'll finish by some future possibilities for extending this work. So why doing Vinograd schema challenge is not so easy. It has a large vocabulary, and the sentences have complex grammatical structures. So on the face of it, the quantum circuits that you get will be extremely noisy. Even if it's possible to get the right parse from an automatic parser, the quantum circuits will take a long time to train. Then when you join the sentences, okay, we've done the spider, general box, but ideally, it should really be a logical operation on the two probability distributions that come from each sentence. So this is a big question for me. I don't know what should that logical operation be. Then we imitated the Fock space, really using an element of Fock space that is entangled, like the general story. You could also work with separable states, and instead of having one big trapezoid, you could have three smaller ones. So I can try and draw. So we would have like something like this. But why not n separate copies? When you project the nth layer of a Fock space, that was our shorthand. And then this was the projection where you get n layers. So this was our shorthand. So why not this one? I know in the past when we worked with similarity-based tasks, that wasn't a right option. But here we are classifying. So it should probably be OK. I wonder if we will have quicker convergence and higher accuracy. So probably we should try. Then the question is, we've been using DiscoPy to a large extent, but of course DiscoPy doesn't do anaphora resolution. So I can show what we've done and how this can be done properly. And obviously a big question from the beginning was how to use DiscoSec to model this kind of phenomena. I've got internship with several of my PhD students with CQ this summer. Hopefully we'll attack these problems. And these are resources. If you're writing a paper, hopefully it will come out in the next couple of weeks. All the code is in a GitHub repository. And I've promised Royal Aquatic Engineering we're going to run a joint seminar with CQ. So hopefully that will happen. I just wanted to show. So if you put the cat broke the vase, it was fragile, to disco cat, the disco pi diagram generator. This is the diagram that you get. Where is Alexis? Hello. Fair enough, so it's connecting the vase to was, which is completely okay because there is no discourse resolution structure here. Ideally, you would like it to be connected to the cat, and the first and the second sentences to be disconnected otherwise, so it's not happening here. So we have a cheat version where, so this is our Disco X or Disco Pro version. So you have the girls broke the vase, it was fragile. Obviously, co-reference resolution is not a solved task parsing wise, so we connect them by hand. We say, look, the referent of vase, the referent of the pronoun it is the vase. So we mention explicitly what is referring to what, but there are ideas of how to connect this into a neural co-reference resolution engine, and then you get the right diagram. So the fragile is the vase. So as you see, we work with this shorthand, that shorthand here. Got 2 copies of the vase coming out. And correctly, it, 1 copy goes to it. And the 2 sentences are disconnected otherwise, right? So you have 2 sentence lines coming out of the diagram. So that's the idea. It can be done in a much more general version. And finally, let's say play here. I would like to conclude just in 1 minute, maybe. And this is what I want to say. Okay, so the conclusion, so the ethos is obviously, when you want to reason about text, you have to consider both structure, so the logical structure, and data, statistics. So the contributions of this line of research is that we want to extend the existing unified mathematics framework, the DiscoCat framework, from sentence level grammar to document level discourse. And we take advantage of CQ's initiative and use both real valued vector spaces and complex valued vector spaces using quantum. What we've done so far, the results, the novelty, is that we use Fox space semantics for Lambert calculus. We improved the accuracy of the UBC's R&D recommender system with not much structure into account yet. And we got convergence with high accuracy on a simplified version of a pronoun resolution task. There is a lot that can be done on the theoretical level, and I know this is not necessary and absolutely not needed for the linguistic applications. Still, I would like to find a complete model for this model. Lambert calculi is an open theoretical problem. Convergence on Winograd schema challenge on a quantum computer would be a nice practical thing to do. Commercialization would be really nice. We will all get some more money if you can really use these quantum circuits to predict recommendations. And then something else I want to say a couple of words about is something we call contextuality. And that is, right, there are connections between language and quantum at the level of tools, so you can use quantum computers. But is this connection a little bit deeper? So everybody agrees that natural language has a contextual data. That's why we have all these ambiguities, but this doesn't stop us from communicating with each other, because we can use the context to disambiguate. And quantum mechanics was one of the first sciences that had to deal with the problem of contextuality face on. So they have really nice mathematical models, including a shift theoretic model that we use to model and reason about contextuality. So we try to use that shift theoretic model to reason about two-word phrase level ambiguities like green cabinet. And this is joint work with Daphne. And she got the outstanding paper award of a quantum contextuality workshop last year. And at the moment, my other student, Ian, is trying to use the same kind of models to go to the co-reference level for the Vinograd-like challenges. John called Bob. He was upset. This is a generally ambiguous reference. We don't know who is he referring to, right? It can be both Bob or John. As a result of this line of work, we found really nice connections to psycholinguistic research I can tell you about later. So that's a nice thing, as the impact can be generated. And that's it. That is it. Maybe I'll put this slide as my last slide. Thank you.
Repeat the question.
Is it basically a coding map, and in which case, since although we can't clone states in quantum, since the parameters of the classical maybe you can reload the quantum states?
Say that again.
My first question is about the bang symbol and whether it is basically a coding map.
No, it's not cloning. Like, I always try to convince Bob, this is not cloning. Please don't say, it's not cloning. There's no copying happening here. You already have all the copies. Thank you for asking this question. I'll buy you a beer later. This is not, it's not cloning. It's projection. It's projection. Where should I? Look, it's projection. Here's the rule. That rule. It's projection. All the copies are already here. Imagine you have a big state which has all the possible copies of a quantum state. And this exists. Like if you look at current research in Fox implementation of Fox spaces using quantum computers, you have an operation that would produce that big space, but it's actually very impractical and totally inefficient. There's a lot of noise around it. But you have all the copies already. The question is, how do you know how many copies do you want? So this we say, well, we will run machine learning to learn what's the optimal solution, what's this n. And my guess is with n3, you already have a high degree of success, already n3. So whenever you have a word with a quantum like the type A, why not immediately put 2 more copies of that? So you start with bang A, so you already have access to 3 copies of n, of S, if you want. They're all in there. If you want to use them, you can use. If you don't want to use them, you don't have to use them. But if you want to use them, these logics give you capabilities to do that, right?
So my second question is...
Let's continue on the copy break.
Sure.
Oh, no.
Yes.
I like this.
and she's going to talk about what is the reach of universality and undecidability.
Okay, thanks a lot. Thanks for having me. I'm very glad to be here, especially after the last edition of QNLP was online and it was such a pity that we couldn't meet. I'm really glad to be here. This is also probably the closest I've ever been to feeling like a priest or something like that. But I'll try to stay here so I don't feel like I'm in a karaoke additionally. Okay, so I've been thinking, together with some people in Innsbruck and so on, we've been thinking about what is the reach of universality and undecidability, and that's what I'd like to share with you today, our latest thoughts and developments. And I'd like to focus first on universality. So for me personally, this story started with the fact or the discovery that some spin models that appear to be simple actually can simulate all other spin models, namely those that appear to be much more complicated, as in the 2D Ising model with fields can simulate models on high dimensional spins or many-body interactions or high dimensional lattices. And in this respect, this is one facet or phenomenon, or at least it is called universality in that paper. Now, I don't have time to tell you about the proof or like the key ideas of that proof, but if anyone asks me, I'd be very glad to share them with you. But what goes on there essentially is the following. You have an object of study, a spin model, say defined on a hypergraph, and this is transformed to a model defined on more particles, like it has plenty of auxiliary variables, but with simpler interactions, like with simpler building blocks. And the statement is that by fixing the parameters of these additional particles and coupling strengths, this second model, this universal model, can simulate the first one. And simulate means something like reproduce the low energy behavior. It has a precise definition, but essentially it means that it mimics the first model. And so we have actual and auxiliary variables. So in essence, this universal model has an extended domain. Okay, you can think of the additional part of the domain as the hyperparameters in machine learning if you want. Okay? And the description of the original model is given, or is instantiated into the values, into the element of this extended domain, okay? into the distribution of coupling strengths and spin configurations of the auxiliary spins. Of course, the jewel of the crown, or the best understood and the best in many ways example of universality, or of the type of universality that I'm trying to understand, are universal Turing machines, which are, of course, a cornerstone of theoretical and practical computer science. And what goes on there is that you have a model of computation, take a Turing machine, but you could take any other, okay? And a priori, you have two things which seem to be very different. One is the program, T. These are the set of transition rules in a Turing machine, and the other is the data, namely which strings you feed the program, namely which question you're asking that program, namely the so-called instance, okay? So if that were all, it would follow that for every different algorithm, you would need to build a new machine. But of course, that's not the case, because there's this fundamental, really important notion of a universal Turing machine, which completely washes out this distinction, because the program is now fixed. There's some fixed set of transition rules, and it can run any simulation at the expense of enlarging the input, right? So part of the input will be the description of the algorithm it is supposed to simulate. So it's a wonderful idea, okay? So what was previously a program is now part of the input. So a Turing machine is universal when it is capable of reading and acting like another Turing machine. That's kind of the threshold it needs to cross in order to be able to run any simulation. So here we again have actual and auxiliary variables, namely the actual input and the description of T. And yeah, we also have we're also somehow using this additional part of the domain of the universal Turing machine to actually say what Turing machine it is supposed to mimic. In machine learning, we find a similar idea for feed-forward neural networks, for instance. Say you want to learn a function in some class, like continuous function. Typically, it's some well-behaved thing. And then there's the statement, this universal approximation theorem, that for any such function, there is a network with one hidden layer. Okay, sorry, for any such function, an epsilon, there is a network on a given number of hidden units and a set of coupling strengths so that the function on the visible units here is epsilon close to your original function. Okay, so in this case, it seems to be a statement about denseness, and also there's something of the basis of a vector space in there going on. Okay, but anyway, so we also have some visible and some hidden units and a distribution of weights and biases. Okay, so they all seem similar, but I would like to understand really how deep are the similarities. I would like to prove theorems and say one follows from the other or not. One is weaker than the other, or they are equivalent, because so much is known, for example, about Turing machines, and the others are new, and I believe that if we were to establish these rigorous links, we would be able to transfer lots of knowledge and stuff. For example, there's a full characterization of universal spin models, but there's no such thing for universal Turing machines. Why? Well, probably because they are different. Okay, so that's what I would like to understand. How are they related? And more broadly, I would like to understand the reach of universality, as well as that of undecidability, which I see as intimately connected. And I'll have time to say just a couple of words about this connection here today. How? I propose to do so in two ways. One is to compare two examples, namely the spin models and the Turing machines. And because I understand both very well, I feel, and I'll tell you how we do it. That's kind of a bottom-up approach. The other one is to propose a framework for universality and try to see how the different examples fit in the framework. And ideally, this framework will also give us grades of universality and let us compare things rigorously. That's a top-down approach. Okay, on the first kind of set of projects, that's what we do. We compare, so we cast spin models as automata, or more formally as formal languages. And we find that they are all at most context-sensitive languages. And what is to be done next, so it seems that the notions of universality are different, and what is to be done next is to cast the morphisms, if you want, or the relations on the side of automata to operations on the side of formal languages, so that we can formally compare their universalities. But I explained some of this in the past editions of QNLP, and so I'd rather move to the new stuff, which is a framework for universality. That's what we're currently thinking about. And I believe we need to do this in two ways. One is conceptually, so that we can connect to maybe more philosophical texts and to linguists and to less formal notions of universality. And the other is formal, or in particular, categorical. We've chosen this framework of category theory, maybe because of you, because of your influence. Yeah, so I'd like to say a few things about this. All right, first of all, about the conceptual framework. Okay, the conceptual framework starts, of course, with the question, what does universal mean? Well, it means relative to the universe. And by extension, that's something I learned from Martha, as a frozen metaphor, it means all-encompassing, right? So this is the key idea. Given a collection C and a relation R that lands in C, U is universal if U, comma C is in the relation for all C, right? So what's important here is that universal is relative to a collection that we will quantify with all, and a relation, which is this encompassing relation. And whenever you find this structure, it's a very basic structure, then you can call the corresponding object U universal. I'm not asking that U be in C, I'm not asking that R be transitive, reflexive, anything nice, I'm not asking that C be finite, okay? It's just a very basic structure, okay. Let us see some instantiations of this structure. Well, in computation, of course, the first one are Turing machines. C is the collection of Turing machines, R is simulation, U is the universal Turing machine. Also, the completeness in a complexity class. If you've heard what NP completeness means, well, C would be the collection of problems in that complexity class. R would be a reduction, which could be a computable reduction if you're talking about RE completeness, or a polynomial time reduction for NP completeness. And U is a complete problem. That also fits our structure. A universal gate set is a little different. In this case, C is the collection of Boolean functions, and the relation expresses that for any Boolean function, there exists a sequence of gates from my universal gate set so that the two coincide. For quantum computation, it's also a little different. U would be the collection of unitaries of any size, and the relation R expresses that for any epsilon, there is a sequence of gates of my universal gate set, which is epsilon close to my target unitary. Okay? So as you see, there are some nuances in the relations. In some cases, there's an existential quantifier. In others, there's not. But they all fit this very basic structure. Universality classes of spin models. Well, C would be the collection of all Hamiltonians. The relation would be flowing under renormalization, and U would be the collection of fixed points. Or the universal spin models, either in the classical or the quantum case. So C would be the collection of quantum spin systems. Sometimes I distinguish, yes, spin systems means finite size. It's a technicality of the proof, but actually it's correct to call it here spin systems. R is a relation defined in either of the papers, not obvious, it's called simulation or quantum simulation, and U would be the universal spin model. In machine learning, the relation we've seen for feed-forward neural networks about approximating a target continuous function, and there's a similar structure to be found in restricted Boltzmann machines, where what is to be approximated is a discrete probability distribution. The basis of a vector space, of course. C is a vector space. The relation expresses linear combination, and U is a set that contains a basis, so a generating set. If it contains a basis, then you say it's universal according to this definition. Or the extremal points of a convex set, or the extremal rays of a convex cone, right, where C is a convex set or a convex cone. R is the relation of convex combination or positive combinations, and yeah, U is universal if it contains the set of extremal points or the set of extremal rays. Well, there's also the universal graph in mathematics, which literally instantiates our basic structure for some relation, which could be like a minor relation or a subgraph. So there's also something called the universal differential equation, which is a differential equation whose set of solutions is dense in the set of continuous functions, I believe. It depends, there are like 3 or so. Okay, now the universal grammar is clearly also an example because in this case, this is the collection of all grammars of natural languages. The relation says, so the universal grammar is not a grammar, it's a meta-grammar. It has 3 parameters. When they are fixed, it specializes to a target grammar. So that is what this relation is expressing. Yeah, and U is the universal grammar because it can specialize to any grammar. Okay, now this is, I think this one is particularly interesting, the problem of universals in philosophy. Very roughly speaking, it's the problem of how we can assign the same attribute to different particulars. It's a very old problem in metaphysics, and some people said, well, different particulars share the same attribute because they both instantiate the same universal. That's what like Plato and Aristotle would say. And others would say, no, universals do not exist, but then they run into many problems. Okay. Of course, so take these universals for these metaphysical realists, which are something very mysterious that lives in another world outside of time and space, and it's immutable and so on. And now, of course, their relation with all objects that share that attribute is one of universality in our sense. What's more interesting is that what these philosophers also thought about is that if you consider the attribute is non-self-instantiating, then they run into problems because it is, if and only if it is not. And this is precisely the core argument of undecidability. So in many of the examples I have in mind, the ones I showed you at the beginning, I think that there is a fundamental tension between universality and undecidability. And quite unexpectedly, this also appears here. So being very optimistic, this link may allow us to, I don't know, maybe say something new is a bit optimistic, but definitely kind of put this discussion and this tension in a broader context. Because this happens also for Turing machines, for example. Okay, we are doing this top-down approach. So what do we learn by seeing how this structure is instantiated in so many examples? Well, we can now, of course, we want to capture the interesting types of universality, but how do we capture that, right? Well, we can ask questions now, as in, which of these types of universality onsets the generation of complexity, which means something like there's a very subtle jump to universality. And well, yes, for Turing machines and for spin models, no for the universal grammar and for the problem of universals, for instance. So we're kind of coming up with a table of properties that each type of universality has or does not have. Or which is related to undecidability? Well, yes, again, the universal Turing machines, and surprisingly, this problem of universals, no for the universal grammar, the basis of a vector space, the extremal points, and so on. And let me just say a couple of words about undecidability. I take it to mean that no system, very broadly understood, can thoroughly talk about itself. And so these limits, what can be formalized, what can be computed, what can be learned, what can be known, what can be said to be true, what can be said to exist. And at the core of all of these arguments, to the best of my understanding, there is self-reference and negation. There is, in essence, the liar paradox, which is very far-reaching and very, very powerful. And so intuitively, the link between universality and undecidability comes from the fact that universality allows for self-reference and often also for negation. And so when one has one has the other. But making this precise is precisely our goal. I'll show you some steps into making this precise very soon. Okay, so oh, here it should say categorical, I'm sorry. Now comes the categorical framework. I'm not sure if it's the same, because I'm not sure if everything can be formalized. So maybe that's a bit of an ultimate question that I have. Yeah. Yeah. I don't know if everything can be captured with the following framework. Okay. So our central object is what we call a simulator, which is a map. Okay, it's a map in a category, but I don't think we need that here. Of the form. So this is to be read from top to bottom. Each of these objects, P, C, and so on, are like objects in the category. So it's a map from programs and contexts to things and context. And it splits into two, called a compiler and a context reduction. And moreover, there's going to be like another map which can be applied to things and context and gives rise to behaviors. And then a simulator is universal if for every thing there is a program such that for any context C, the simulator on that program behaves like or mimics the thing itself for all contexts. Perhaps it's not so crucial that you get all details. Maybe the main idea here is that this can be formalized in terms of some simulators. Okay, and we also, we relate simulators and we grade, we can say this one is stronger than this other one. But I won't have time to explain that, because what I think is more insightful is to see a couple of examples. The Turing Machine. Well, the programs are the set of programs. T is the universal Turing Machine, which can be taken to be a singleton. The contexts are the inputs to the computation. And kind of the key thing that happens is that SC, in this context reduction, the program becomes part of the input. It's what I explained earlier about the program being paired with the input into a longer string, and that playing the role of, well, doing both jobs, describing what is to be simulated and the input. And the behaviors are the outputs to the computation. Like whatever it is, these are elements in sigma star, where sigma is a finite alphabet and star is the clean star, whatever you may want it to be. Also, a universal spin model is an example of that. In this case, the programs are all spin systems. This compiler is what casts an 8-dimensional Ising or Potts model into a 2-dimensional Ising model. There is a map there, right? There is a map saying which coupling strengths I'm supposed to choose, how I'm supposed to organize them, and so on. Well, that is the job done by this compiler. And so T is the spin model. The context, remember it was previously the inputs to the computation, now it's a set of spin configurations. They play a similar role. Yeah, SC gives the spin configuration, and the behaviors are now the energies. It's what's observable at the very end. It's like the output of the computation. But also a dense subset is universal in this set. We have other examples, but this one is kind of funny. If you want to express that the rationals are dense in the reals, then you can do so by choosing as the programs a rational and a precision, as the compiler simply inclusion into the reals, and the evaluation is going to map a real and a precision into an open ball around that real with that radius. And so the statement that every real can be approximated by a rational maps to or translates to the statement of universality of the rationals in this setting. Okay, and now a few words about undecidability. And because that's something we can do with this categorical framework. Okay, so a function, or a morphism if you want, doesn't matter, from two objects A cross B to C is said to be weakly point surjective if for any G from B to C, there is an A such that f of A is the same as G. Okay. So this dash here means for all inputs, for all little b's in big B. Okay. So in other words, so the last part of the definition can be said, you can say it as the fact that A or F can represent G if there is an A that you can put in the extra part of the domain of F so that the two behave the same. And then F is weakly pointer-ejective if it can represent every G. Okay? Now, Levier's theorem says that take a function that is weakly pointer-ejective from A cross A to B, then every G has a fixed point. So in plain words, if the function is weakly pointer-ejective, then the G's cannot be too expressive, cannot be too general. Why? In order to avoid a contradiction. Okay, so the contrapositive form of this theorem would say if there is a G without a fixed point, like negation, then F cannot be weakly pointer-ejective. And weakly pointer-ejective is like universal. Essentially, it's the same, and that's what we're trying to make precise. Look at what we're doing. We're enlarging the domain of F and choosing an element in this extra part of the domain so that FA behaves like G. And Levier's theorem is the statement of undecidability. Because Gödel's theorem, the halting problem, this sentence is false, many others also, the fact that P and NP cannot be separated by means of an oracle, Cantor's theorem, all of these follow from Levier's theorem, can be seen to follow from Levier's theorem. So in particular, for linear bounded automata, which are the next type of automata, which are weaker than Turing machines, we show that eval, our function, cannot be weakly pointer-ejective. In other words, there is no universal LBA, and therefore they are not bound to undecidability. But of course, for Turing machines, their eval is weakly pointer-ejective, so there is a universal Turing machine, but then they are bound to Levier's theorem. In what form? Well, in the sense that there are undefined points, namely non-halting points. Namely, Turing machines can only compute partial functions. So I think that the trade-off is transparent here. And that's what we're working on now, and trying to understand this better. Okay, am I too early?
Speak slower if you want. We've got 10 minutes.
Oh, 10 minutes?
Yeah.
Oh, then I'll finish earlier and I'll let everyone ask questions and we can discuss. Okay, we're trying to understand what is the reach of universality. And the first way how we're trying to approach this question is by comparing two examples, more specifically by casting spin models as formal languages, where we found, I didn't have time to explain that, where we found that effectively zero-D spin models, the language of effectively zero-D spin models is regular, the language of 1D spin models is deterministic context-free, and the language of all other spin models is context-sensitive. And so that gives us in particular a new complexity measure for spin models that measures somehow the hardness of the local structure of the model. In other words, the grammar of physical interactions. But in particular, it implies, since 2D spin models are universal, in our sense of universal spin models, but, sorry, I forgot to say, Turing machines recognize recursively enumerable languages. As you can see, there is a mismatch. It seems that they are not at the same level. It seems that universal Turing machines are stronger. And that's what we need to understand and to figure out. And the second way to tackling this question is by developing a conceptual and a categorical framework for universality. In the conceptual one, the central idea is that universal means all-encompassing. And we have instantiated that in many examples in many disciplines. And the second one has as a central object some simulators that can do some things, and I showed you a couple of examples. And I could end here or end with a provocation. Okay. So I really wonder, what are we to make of these limits of undecidability? Are we supposed to accept them? What are they telling us about everything about the world and the fact that they are so strong? And I don't know how to make sense of that. And one thing that I don't understand is the fact that art seems to overcome some of these limits. As in, you can do self-reference and negation in art. And also, clearly, our brain can understand that the liar paradox is a paradox, whereas a computer cannot. And yeah, some people have thought that, that it follows from this observation that the brain is more powerful than a computer. I think that's too quick of a conclusion. But I would like to understand yeah, the implications of all of these thoughts for, I don't know, for our thought, for art, or yeah, things like that. Thanks.
Vincent was first. Do you want a microphone or can you speak loudly?
How's this? This good?
Audible?
It's fine with me.
All right. Thanks for the talk, Gemma. Could we go back to the simulator diagram along with the evaluation?
Yep.
Yeah. Yeah, any of those are fine. So why do we need all these different parts? Do they ever show? Do we ever work with one of the parts in particular, or if we're always considering them all together, then do we need all these little boxes?
Well, they play different roles in the examples, and we seem to need this structure. Perhaps it could be done differently, but that's the way we've come up with. But it doesn't seem like we can do with less.
Because the fixed point theorem only takes the inputs and the outputs of that box. And if you were to just if you were just to black box that entire configuration, then you get out something that's very similar to the normal computers and what Dushko's doing is this idea that instead of having a different concept type for every evaluator, you just have a universal program type that gives you all the behaviors that you want. So I'm just wondering what extra is one by sort of breaking up the idea of a universal evaluator into these different components that do these different things, copying the program, handling the context, etc.
Okay, that's a very interesting comment, and I didn't understand many of the things, so I would really like to go back to it. A priori, I would guess that the answer would be that our sorts of universality are more general than that of universal Turing machines, as in they include many things that you wouldn't usually call universal. And I don't know if these are covered by this structure that you're mentioning. But I would definitely like to go back to that. Maybe another minor comment is that we here consider whether eval is weakly point surjective. So we apply it to this part of the framework. I don't know, I'm very interested in what you're saying. I'd like to understand it better. Yeah, thanks. Thanks for the comment, yeah.
I think Ross was next.
Yeah.
Jem, could you repeat the question?
Oh, yeah, I can repeat the question.
Yeah, thanks, Jem. So your conceptual idea of universality is really close to the categorical definition of an initial object or a terminal object. So object and everything else is related to from.
Yeah.
So is your categorical definition also initial or terminal?
Yeah.
Like that?
Yeah. Thanks for your question. Yeah, the question is that the conceptual idea of universality is very similar to an initial or a terminal object. In other words, something that is on top of a preorder or underneath a preorder. Yeah, that's how we started. That's how we started. But eventually we made it more abstract for a set of reasons, which we thought captured better the gradation of universality, and ended up having this simulator as our central object. But I should have mentioned that, of course, yeah, that conceptual idea of universality is the same as being on top of a preorder. where encompassing is the relation in the preorder. Yeah.
I guess a follow-up on the same question is, so your definition is on a relation, so you only have at most one arrow between any two things, or it's a preorder. Have you considered looking at categories where you have more arrows between objects than this one?
Yeah, the question is whether there can be more arrows between two objects. At the conceptual level, we don't even need category theory. I mean, it's so simple that I don't think we need it. So it's so bare, the structure that we have at the conceptual level, that yes, there could be multiple arrows.
I guess then you would add like maybe a unique arrow.
I don't even think you need a unique arrow. It can be a very dirty kind of universality where many things are redundant or there are multiple ways of getting to the final point. I should have said that the trivial simulator is the object where the simulator is the identity. And that is universal because you have the set of all things, and so they trivially encompass everything just by being themselves. So that plays a special role in our category also, and actually that allows us to define stronger kind of universality if you can go from one to the other but not from the other to the one, namely from one to the trivial one but not from the trivial one to your first one.
Okay, there's a question here and then after that.
Yeah, so this makes me think of categories and the notion of bimodule and profunctor. So actually, I think Levier's name for it is bimodule. So basically you have a sort of generalized type of relation, just like you have. And for example, bimodules, you can compose them. So there's a sort of structure to these relations. You can compose them one after the other. Does that come into play in your...
I don't know, because I'm a beginner in category theory. I don't know, maybe.
Okay, yeah, because
you have a structure in where?
I mean, you can take one such relation and you compose it with another. It's like if you have a module over two algebras, A and B, then you have another one over B and C, and you can tensor them over B, and you can compose them, so you get this composition structure.
I wouldn't be surprised. We're at the beginning of really exploiting and developing this structure. Yeah. Thank you.
Anush?
Yeah, thanks for the question. It's also very interesting. I mean, in my words, you're saying that the liar paradox cannot be fixed. As in particular, you can formalize this with Turing machines by defining the so-called arithmetical hierarchy of, right? Imagining you have a Turing machine with an oracle that solves the halting problem, then a super duper Turing machine. That there's always something that escapes. There's always a new halting problem you can build, and which makes you go kind of higher in that hierarchy. And for every level, there is some form of universality, some form of completeness for that class, like RE completeness or super duper RE completeness. And for every level, there are some things that escape that level. So there is always this tension between the two that I don't understand fully. But this should be expressible in this framework too, and we haven't looked at that yet. Thanks. Yeah.
We're going to have to stop there, but there's a coffee break after the next talk. So let's thank Gemma again. And then I hope the next speaker can come over. Okay, great.
Así.
speaker is Armando Galante from Milan. He's going to talk about quantum data representation.
Okay, so hello everyone. First of all, thanks for having me. It's a pleasure to be speaking at QNLP again. And today I'll be presenting quantum data representations for audio natural language processing, although we'll see that the audio world could be replaced with signals in a more general sense. But yeah, let's start and see. So I am actually pursuing a PhD in quantum computation at Politecnico di Milano, and what I do in my PhD is searching for quantum data representations. So I work with fault-tolerant quantum computers, meaning that I don't generally do experiments. I work for far-term quantum algorithms, and I try to quantize data representation algorithms and bound the runtimes of those algorithms, meaning that I don't usually deal with VQE or QAUA, but with other routines in the gate model. So this field is very close to quantum machine learning, and it's actually it's maybe a subfield of quantum machine learning, and I would like to stress the importance of finding data representations. That's because even though, say, in one day we won't be able to gain exponential speedups for quantum machine learning, if we get polynomial speedups for data representations, that is still interesting. Because maybe we don't get speedups in the computation of the machine learning algorithms, but if we allow to transform our data in new feature space, and we can do this with a polynomial advantage, meaning that we can afford some new transformations that we couldn't afford classically, we might allow simpler models to learn better stuff. So we might improve the accuracy of our models. And in particular, today I'll be talking about two data representation algorithms. The first one I'll be presenting is an algorithm to find sparse representations. And the second one is there are some SVD-based methods. So I already discussed some of them in QNLP 2020, but we have some updates. So let me convince you a bit about the importance of data representations again. Say that you have a data set. This is a simple data set, so it lives in one dimension. And this data set has two labels, a label 0 and a label 1. And if you picture this data set, it looks like that. And your model is a very simple model. You have a function, the function takes a point, and it outputs the label of the point. So either 0 or 1. But the model basically outputs the class by just comparing your data point with a threshold. So basically the question of whether this model can correctly label your data is, can I set a threshold in this line such that I correctly classify those points? But this is problematic because, of course, when you set the threshold somewhere, then you're gonna have that you cannot linearly separate those points. But then, what happens if you transform your data in a new feature space? So you just squared your data points. Now you have a parabola, and if you project those data points on the y-axis, you have something like that, and now your model can correctly shatter the points. Okay, so we kept the model simple, but we are dealing with data in a new feature space, and that's what it's about. Okay, so the first part of the talk is about an algorithm for learning sparse representation, and it's called the matching pursuit algorithm. We have the following problem. So we have a signal. In this picture, we have a continuous signal, but you can imagine to have a discrete signal. So you sample it, and then you have a vector of a fixed dimension. And then you have a bunch of vectors, and you want to express your signal as a linear combination of this set of vectors. The fact is that you have more vectors than what is needed to span the space. So you have multiple solutions that approximate your signal, or that reconstruct your signal, but you want to find the sparsest. So you want to find the sparsest linear combination of those vectors that approximate your signal. And there are cases when signals are sparse with respect to some set of vectors. For instance, this is a medical application. This is a ECG signal. And here you have the DCT basis. So this is actually a basis. It's not, it's not the problem of learning sparse representations yet. But you see that if you transform the ECG signal in the DCT basis, then you have a vector which has only a few non-zero components and a lot of zero components. And the whole family of vectors acts like that. So the whole family of ECG stuff is sparse with respect to this dictionary, to this set of vectors. This is nice because you can use these. If you can represent your signal as a linear combination of, a sparse combination of stuff, then you can use this sparse representation for several applications. So the first one, for instance, is data compression. And this is actually how JPEG works, for instance. So if we agree on the set of vectors that we want to use to represent our signal, then instead of communicating you the whole dense signal, I can just communicate the non-zero components. And you'll be able to reconstruct the original signal. So this is useful for signal coding, audio coding, or signal compression. This is also useful for signal reconstruction, denoising in painting, which can be used for audio too, because say white noise, so I add white noise to my signal, and basically this sparse representation is acting as a compression, but you cannot really compress white noise, meaning that in the sparse representation you will have a lot of little spikes. You threshold them off to 0, for instance, and you transform in your original domain, and you can perform denoising. Or there are a couple of nice papers from Terence Tao and other people about super resolution, and then you could actually reconstruct your signal in frequency, or you can see it as a kind of a Fourier transform. You could reconstruct your signal in frequency even if you don't have enough samples to reconstruct your signal. And then you can assume that different distributions of signals, so different families of signal, they are sparse with respect to different vectors of your dictionary. And basically you can use the spectrum as additional features for your machine learning algorithms. Because if you have two families of signal that are sparse with respect to different vectors, then you can just compare the spectrum and find anomalies, for instance. This is, for instance, super nice in this example here. If you put a spike there, which is an anomaly by the sensor, you would see that the spectrum significantly changes. Okay, so in a more formal way, you have a vector, which lives, for simplicity, it's a vector of real numbers of length n, and then you have a set of vectors. The set of vectors I was speaking about, it's called dictionary, and those vectors are called atoms. You can assume them to be unit, like of unit norm. When I mean unit in L2 norm. And you also have a reconstruction error, meaning that you want to reconstruct your signal, but your reconstruction is like in an epsilon ball from your original signal. And the problem is formally defined like that. So it's a constrained least square optimization, where the constraint is on the sparsity of your solution. So you're minimizing the L0 norm of your solution. Unfortunately, this problem is NP-complete. So if I want to find the optimal solution to this problem, then I'll need to waste a lot of time, a lot of computational time. But in practice, since this finding sparse representation has a lot of useful applications, there exists a number of greedy algorithms that can tackle this problem with suboptimal solution in polynomial time. When I mean polynomial in the number of atoms and in the signal length. And so there are a few greedy strategies. One of them is the matching pursuit algorithm, which is the one that I'm going to present soon. There is the orthogonal matching pursuit algorithm, which is very similar. And then there are a number of L1 relaxations of this problem. Like instead of minimizing the L0 norm, many people optimize the L1 norm. And in some specific case, you can obtain the optimal solution. And there are also a number of interesting related problems that are like about dictionary learning. So you are given a signal and you want to learn the dictionary for which your family of signal is sparse. And those family of, dictionary learning problems use those other algorithms as subroutines usually. Okay, cool. So this is the matching pursuit algorithm, which is the first one that I decided to tackle. And it works like that. So it iteratively updates the solution. And again, it is suboptimal. So what it does is it stores in memory a representation of the residual, which is the part of the signal that your solution hasn't approximated yet. Then you have your solution at the beginning is at 0 vector, and you iteratively update the solution. So at each iteration, you update the solution and the residual. The way you update the solution and the residual is in this place here. What you do is you take the inner product of all the atoms with your signal, with your residual, and you select the atom that produces the biggest inner product in absolute value, just this step here. Once you've found this atom, which is the best one at the current iteration, you can use it to update the solution and the residual. And then the stopping condition is either when your solution is not sparse enough, meaning that the algorithm is failing because it's greedy, again, or when the residual has a small norm. That's because you are already in this approximation area. So these are two stopping conditions. Now, the slow part of the matching pursuit is exactly this stage, which we call the sweep stage, because we are sweeping all the atoms to compute the inner products. And this exactly has complexity k and m, where, because you're computing m inner products of vectors of length n, hence why this term, and you're doing it k times, where k is the number of iterations. You can think of k as L, like the sparsity threshold, more or less. Even though the matching pursuit might update the same index of the solution multiple times. So k could be a little bit bigger than L, but it's O of L, let's say. In the orthogonal matching pursuit, they fix that and they only update one solution at a time, but you have to solve an additional least square problem over there. So the idea is to have a quantum algorithm that speeds up this sweep stage. And we do it in this way. So we only want to prepare quantum access to the dictionary and to the residual. Then we will store the solution classically and update the solution classically. So in the end, we will have a classical representation of the solution. Then we want to compute the inner products between all the atoms and the residual in superposition. And the strategy is to use basically Grover search on steroids to find the maximum absolute value to get a polynomial speedup. Okay, so I'll take again some concepts that Alessandro presented this morning and introduce them again. So to prepare quantum access to the dictionary and the residual, we assume the existence of a QRAM, which is basically a device that works like that. So you have a place where you can store your classical data. And of course, like those are memory cells and they have an address. What you want to have is a circuit such that you have two registers, you input the address in the first one and it gives you the binary encoding of what you wrote in the memory cell in the second register. And you want this unitary to act in superposition on all the possible addresses. So that's the assumption of a QRAM. And as Ale was saying, there are a couple of proposals for such QRAM. The first one was from Giovannetti, like the Bucket Brigade one. And recently, Han had some nice results on the error resilience of the QRAM. So that's the only strong assumption that we make. So if you have a QRAM, what you need to do is say you have a residual. So you have the residual at the beginning. You want to create this kind of access, which is you have a zero state, sorry, and your unitary needs to create an amplitude encoding of your residual. The way you do that is you build this structure here, this tree, which is called a KP tree. You can find some references on, in here. And you need to store the entries of this tree in a QRAM. If you store the entries of the tree in a QRAM, then there is a procedure that performs this mapping or that mapping over there in logarithmic time. So if you have a vector of length n, in log n, you can create that state. So that's the input. So we will have our representation of the residual will be stored in this KP tree in RAM. So when we update the residual, if we have to update the whole residual, we will have to pay the time of updating the whole tree, which is n log n. Using the same kind of tree, you can also build quantum access to the dictionary. And building quantum access to the dictionary means having a unitary such that you query a column. So you query an atom, and it gives you an atom here, where the atom is amplitude encoded. And basically, by combining, again, those trees in QRAM, you can build such a quantum access. And the time, it's just, the query time is logarithmic. The storing time is linear in the size of the dictionary, more or less. It's a little bit super linear. But you only need to store the dictionary once, and it's read-only. Like, you store it, and then you have this, that the dictionary will work for a whole family of signals, and you don't need to update it anymore. So, okay, we created quantum access to the residual and the dictionary. Now, giving access to those two unitaries, we can use a procedure that, again, Alessandro presented this morning for distance estimation. It's a procedure that was presented also in the Q-means paper. Again, basically, Hadamard tests on steroids in superpositions. And from these two quantum accesses, you can create this quantum state here, which is a uniform superposition that has two registers. One of the two registers is the index of the atom. So here you are indexing all the atoms. And here you have the binary encoding of the inner products, between the residual and the atom. And you can build this superposition, which is a uniform superposition. And the procedure is quite fast, like it's by logarithmic time to query those states, some terms that depend on the probability of failure, and you are linear in the error of this encoding here. Once you create this state, you can use this other routine, which again, it's basically using Grover multiple times with different oracles. So you use Grover a number of times, but you always change the oracle that you use to perform Grover. And you can find the maximum absolute value of this state in time, which is square root of m, which is square root of the superposition. And yeah. So in the end, if you chain together those routines, you get this kind of runtime here. So instead of KNM, you have this term here, which is given by the update of the residual, because you might have to update the residual in QRAM at each iteration, plus k times the search for the inner products and the time to create the inner products. So usually this is the leading term, but of course you have a dependency on the error as well, so you need to be careful, on how much error your application can tolerate, and this will depend on the dictionary too. Usually, the speed up is something like that. So these are rough estimation. You can find more experiments in the paper itself. So we are working on other algorithms that are based on the matching pursuit one. Another one that we are working on with Stefano Veneri and Stefano Zanero, who's my advisor, is a version of the matching pursuit where the input state is not a classical vector, but you have a procedure that generates this input state S. So you won't have the residual stored in QRAM, but you need to do everything with circuits, and you have that the dictionary is block encoded. And then we're working on other versions, which are a version of the orthogonal matching pursuit. There are a number of algorithms that could be interesting to investigate, like adding constraint to the orthogonal matching pursuit you can resolve in painting problems, like audio declipping problems. Or, yeah, also L1 relaxations are interesting to check. And again, same for KSVD and mod. Those are dictionary learning methods that are based on the subroutines that we are building. Now we go on the second part, which is about the quantum SVD-based techniques and can be applied to natural language processing tasks. So instead of using here the concept of sparsity, we're using a similar concept, which is, I mean, the application of SVD in natural language processing are well known, and you have that many problems in machine learning, I mean, many data sets in machine learning are low rank. So if you look at the distribution of the singular values of your data set, it looks like that, like the decrease exponentially. And in natural language processing, if you build a matrix like that, which is a bag of words, basically, so you have the documents on your rows and the terms on your columns, you just put the frequency of the word for the document in each cell, and you take the singular value decomposition of this matrix, you see something like that. Like, this is actually taken from a data set, which is like a set of titles of conferences. You produce the bag of words, you take the SVD, that's what you get. And you can exploit this kind of sparsity to learn things about your corpus. Let me define something which might be also important. Like, of course, you know that the singular value decomposition acts like that, so you will decompose your matrix in an orthogonal matrix, a diagonal matrix, and another orthogonal matrix. And you have that the singular values are the ones that are being plotted here. You also have these terms that I will call factor score ratios. They are basically the square of your singular values under the square Frobenius norm of your singular values. They give a measure of the importance of the singular values. And we will be using them soon. So in QNLP 2020, I presented some SVD, quantum SVD-based techniques to build the models of principal component analysis, latent semantic analysis, and correspondence analysis. And I presented those three case studies. But today I'm going to present some other algorithms and extensions that you can use, and then I'll show you one example of how you could use those subroutines to apply those subroutines to QNLP. So again, the toolbox that we are going to use is similar to the one that we used before and to the one that Ale presented. So we have that data will be stored in a Theorem, and we have the same access model. Then we only need a few operations, so we need to be able to do quantum arithmetic operations and singular value estimation, which is a routine like that. I'll go back to that soon. Amplitude estimation and amplification, and then you need to do tomography on the states because you want to reconstruct the vectors. So basically, the core of this, using those routines, using this toolbox, you can build a framework that helps you retrieving a lot of information on the left singular vectors, the right singular vectors, the singular values, the factor score, and all those infos here. And everything is based on a simple idea, which is this singular value estimation one. So you are given a vector that you can write as a linear combination of the right singular vector of your matrix. And basically, you have a unitary that maps in another state the singular values that correspond to those singular vectors. If you apply this routine to the state of the matrix itself, you can create this state here, where you have that the singular values are written in their binary encoding, and the singular vectors are written in their amplitude encoding actually. So performing the tomography on this state is a bit messy, but that's not what we need. The important stuff is that creating this state is quite fast, so it's linear in the approximation of the singular values, and you have this dependency on mu of A, which you can think of as a norm of A. It's like a Frobenius norm or something like that. There is a proper definition, of course. But the cool stuff is that if you have this state here, this state basically acts as a slot machine, where if you measure the third register, you get the ith singular value with probability which is proportional to the factor score ratio, so to the importance of the singular value itself. And so you're basically sampling the singular values from this distribution. So this is the distribution of the factor score ratios of the same data set that we saw before. So of course, the shape remains the same. And you basically sample the singular values according to their importance. On the simple intuition, last year, actually 2 years ago, we presented those kind of algorithms. So algorithms to extract the singular values, the factor score and the factor score ratios, some algorithms to extract the right singular vectors and the left singular vectors. And we bounded the runtimes of those algorithms. But let me go to the new algorithms that we designed after those ones. So the first of all is this one. So here the problem is you are given quantum access to the matrix A, and you know how much variance you want to retain, which basically means, the factor score ratios, if you sum them up, they sum up to 1. And you want to retain a piece of those, of those singular values there, and this is how much variance will be explained in your data representation. So you know where to set this threshold. This is an input of your algorithm. But you don't know what's the threshold for the singular value. So you know that you want to retain 30% of the variance, but you don't know which singular value allow you to gain the 30% of the variance. Then we have an algorithm that allow you to estimate this threshold theta that you will use to separate the singular values in this runtime here. And the idea is basically that what you can do is you set a threshold theta on the state that you saw before, and you do a controlled rotation on another ancillary qubit. You set it to 0 or to 1, depending on whether the singular values are bigger or lower than theta. Then you perform amplitude estimation, and you get a point in this other space. And you compare, like, if the point is near to the number, to the variance that you want to estimate, then you just stop. Otherwise, you do binary search. Then you have another algorithm that allow you to estimate the reduced rank. So say that now you know the threshold that splits the singular values. But you want to learn how many singular values are there. So say that this is like topic modeling, because singular values and singular vectors allow you to find the most relevant topic in a data set. But say that you want to count this number of topics, for instance. So the number of topics that explain 30% of your variance. Then you can just use your threshold to perform a Grover counting algorithm, and you will have this runtime here, which has, again, a polynomial speedup on its classical counterpart. And finally, we have another algorithm that, given quantum access to the matrix A and the top k singular vectors, builds a quantum state which is the projection of your matrix A onto those singular vectors in this time here, which is quite fast. Like, it's just linear in the Frobenius norm of V, which is bounded by square root of k, and where k, you can think of k as the number of topics, for instance, so the number of singular values that you retained. And then the square root of p, usually you want to retain a variance which is 30%, 50%, 15%, but basically this is a constant. You can think of it as a constant. It's rare that it's approaching 0. So with this tool set, you could think of some experiments like that. I present you a toy example that you can use. A toy example for those routines. So I had a data set with some news, and I took 40,000 short description of those news, roughly 10,000 words and over 31 categories of news. And that's the plot of the singular values, again, so you see they decrease exponentially, even in this setting. The idea now is we learn how many singular values are relevant, so how many of them are enough. You just extract the top k right singular vectors. So this was done classically. And then what you do is, for each document, you project it onto the, each singular vector, each right singular vector identifies a topic. For each document, you project it onto your topic, and you see how much of the norm is preserved. You take the top 5 documents with the maximum norm, and you plot them. So you just see them, see what topics there are. And if you do that, the first topics yields a lot of yikes and ouch. That's because, yeah, probably I should have applied more preprocessing to the data set, but it's still interesting. It still performs like a kind of data analysis. Like I could, after this, I could know that I should have preprocessed the data more. Topic 1, for instance, seems to be things that are being reported by people. Like, I felt like I shouldn't have said what I said, the senator said, and here said is a bit leading the topic. So the topic is about stuff that has been reported by other people. That's what it seems to me. Then there is another topic which is about Trumps and politics, apparently. And I thought that it was interesting, but till now I had the doubt that this model was basically overfitting on some words, like Trump, and said in the previous the previous slide. Then there was this 10th topic, which is a bit more interesting, which was basically connecting women and rights. So it's not only about women. You can see the word women in every sentence, but I couldn't find a word that talks about rights that is always repeated in those news. But, you could definitely see the stuff, the flow. And so with our quantum model, what we can do is, when we have our data and we extracted our singular vectors, we build quantum access to those singular vectors, and we project our matrix onto the singular vector that represents the topic. So now you obtain a matrix from where you can sample each sentence by its importance for the topic. So you just sample the state, you get the index, you go check your data set and plot the sentence and have a look at those topics. And so that's okay. So that's something you can do. And you can do that quite fast because mu of v, if v is only one topic, it's equal to 1. And if you check like the square root of the ith factor score ratio, if you check the 50th one, it's 25, which is okay. Like 1 over 25, it's quite doable and fast. Okay, and you can do that, of course, for the several topics. So say you have your singular vectors, then you can fastly perform the mappings on your quantum computer. As a last thing, I would like to say that, again, we saw that all of our runtimes depended on errors and probability of failures. And when we designed the algorithms, they weren't thought specifically for NLP. They were thought as routines that you could use in several places and frameworks. Like, it's basically a framework for SVD-based data representation. You can use it for multiple applications. Now, the problem is we actually need to enable data scientists. Like, I'm in Politecnico di Milano, and my university is full of engineers. There are no proper courses on quantum computing yet, but there are a lot of engineers that are able to do data science. And if we gave them access to those routines, they could understand. I mean, they could find nice applications of those algorithms and study for which kind of applications those are useful. And that is why, like Ale presented at the end of his talk, we developed this framework where you can basically analyze the runtime parameters for a specific data set. So you take a data set, you have our runtimes, and you can estimate those error accuracy parameters and probability of failures for your specific data set. And we basically forked scikit-learn, so it's easy to use for data scientists. And we are having students trying that to find application of quantum computers, where quantum computers could have the practical advantages. Because then you estimate the parameters and you get an idea of how many features and how many samples you need for the problems to be efficiently solvable with quantum computers. And if you discover that in your application the number of features is not reasonable, then maybe it's a good area. And that's the end of the talk. So if you have questions, I'll be pleased to answer them. Should I? So is the question about the experiment? Sorry, I didn't hear. Did you say state copies?
Do you get the same topics via classical and proper SCD?
I see. So, I'll wait.
Do you also repeat the question?
Sure. So the question is, would you get the same topics if you did experiment quantumly or classically? So the short answer is, I haven't tried the experiment. But the long answer is, yes, because you can always do that, because you can arbitrarily choose the error parameters. So asymptotically, you can go to error 0, but you pay some runtime. So the goal here is to characterize if for your specific dataset and application, you can have some error that is tolerable. And that is why we propose that framework. So asymptotically, yes, you can get exactly the same topics, because you get the error to 0, and you do that. There will be a threshold for which the error doesn't count anymore. But again, it depends on your specific data set. That's why we were thinking of that framework. I hope that was clear.
In some applications, people replace SVD by things like non-negative matrix factorization, because SVD has this annoying property of if cat and space are not about politics, then they are similar. We have negative interference. I wonder if some of these algorithms could work in the non-negative case as well.
So you're saying that some people, instead of using SVD, use other matrix factorization computations, and the question is if we could use them too?
Yeah, if you could adapt these quantum algorithms beyond just SVD to other matrix factorization, or how dependent is it on?
So the question is if we can adapt our routines to run for those other algorithms. Well, I would say that it depends on the factorization algorithm. So you need to actually look at the factorization algorithm and see if it works in a similar way. For instance, I think that the QR algorithm doesn't really work in this way. Like, as I said before, the main routine of our algorithm that allow us to build the whole framework is this one that creates the entanglement with the singular values and the singular vectors. This is a routine that very similar to what Patrick Rebentrost and Lloyd presented in 2014. And we just use this simple idea here. So if in other factorization method you cannot use this idea, which runs exponentially faster than any other thing, maybe you need, you can devise some other algorithms, but not with the same framework. This framework is specifically set for singular values. But yeah, I would have to think more about that. And
okay, if there are no more questions, let's thank Armando again.
Thank you.
our session. So first we'll have Yannis Vlasopoulos, who will tell us a proposal for modeling language semantics given probability densities of text continuations.
Okay. Okay, can I be heard? I can be heard, okay. Okay, thank you very much for the invitation. It's great to be here. So what I'm going to try and talk about is, we have this evidence lately that systems that learn text continuations, learn basically how to complete text. So you just give them raw text, and you hide a few words, and then you train the neural network, which is usually so-called transformer, to fill in the gaps. Then it can actually produce text and do some interesting tasks. And it seems that it learns some part of semantics. So it can produce text which is syntactically and grammatically correct, and which is internally coherent. But you can never, of course, be sure that the answer you get is going to be right, given some predetermined corpus. So that's a big question. That's a big problem. And it's more like a hallucination in a way, right? So, and actually, you can find applications online where they sell it. Like if you're a writer and you get a writer's block, then go to our apps and we'll help you. We'll help you get over the hump. So, but the question is, so the question I want to ask is, what part of semantics is hidden inside these text continuations? It turns out actually that, in category theory, there's already a kind of structure that deals with part of that question. But the question is, okay, of course, I'm talking about category theory, so where's category theory here? I mean, there's a lot of category theory already been mentioned. Well, so to start with, I mean, we know that this is the distributional hypothesis is pretty old. So the idea is that texts that have similar use, they have similar meaning. So if words are used in the similar context, then they have similar meanings. Or you can say something about their meanings given the context, basically. And this is called the distributional hypothesis, statistical semantics. And this has been implemented in such old things, like, things which are, tested, like latent semantic analysis and word2vec. And in word2vec, for example, you have basically this matrix, which is the probability of a context and a word, divided by the probability of the context and the probability of the word. You take log of that, shift it by something, and then you do basically what it does is a matrix factorization of this matrix. And there's other versions where instead of using this measure of probability, you use the conditional probability. These transformers, they learn such distributional statistics. They learn basically the conditional probability of continuation. And so the question is there some underlying structure that encodes some part of semantics? And so what I want to propose is that there is one, actually, and it's a category enriched over the interval. The interval thought of as a monoidal category, where the monoidal structure is just the product. And then, of course, you can easily transform that to a metric structure. So, and that basically, that's the first part of the story. So this talk is going to have two parts. The first part is going to be about this 0-1 probability category. And at the end, we'll see how this is related also to something called tropical geometry. Or maybe some of you know it as the max plus algebra. It's a semi-ring. And that's joint work with Ty Bradley and John Torilla. And the second part of the talk, of course, because we're doing quantum stuff here, I want to say something about how we can implement this theoretically, of course. If we have a state, which is kind of the state of the language, in a way, make basically a functor from this initial category that I'm going to talk about, which is enriched over 0-1, to another category where the objects are basically positive operators, densities, reduced densities. Okay, so first, the baby version of that is to think of language as a poset. So how can you think of language as a poset? You can just say that the objects are the texts, and then in one text has is smaller than another one if the first one is contained in the second one. So this is an associative relation. And what is a poset? Just a poset, you can think of it as a category enriched over the Boolean algebra 0-1. Okay, so for every, so if one text is encoded in another one, the morphism is basically 1 inside this Boolean algebra, and if it's not, then it's 0. And the composition of arrows is precisely the product inside the Boolean algebra. Okay, so if one text is contained in another one, then we associate 1 to it, but then if the second one is not contained in the third one, then you associate 0. 0 times 1 is 0, so that gives you the composition. So we start with this posted structure, and that seems pretty innocuous, but already, actually, we can make some conclusions out of it. So what basically, this is a very standard classical idea. You have your posted, and of course you want to complete it. You can complete it to a lattice, so you can make a lattice completion. And the idea of, in this case, is that you associate to an element in the posted, you associate its ideal. The ideal is all the things that are greater than that element. So in this particular case, for example, if we start with red, then the ideal will contain things like red rose, red blood, red apple, and so on. And so the idea is that this ideal actually contains the meaning of what red is. And of course, if we want to be more categorical theoretic, we just think of this as a function. So for every text x, we have a function bx, which is evaluated on any other text y, and it gives 1 if x is included in y and 0 otherwise. Okay, and so to prepare, so if you think of it as a category, this is the this is called a pre-sheaf. It's the pre-sheaf associated to this object x. And so this is a classical construction where you go from a category using something called the Yoneda embedding. Many of you probably have heard about this. And you go into the category of sheaves, or pre-sheaves actually we have here. The category of pre-sheaves is always better because it's complete. It has limits, co-limits, and not only that, but it also has inner home. And the inner home, actually, you can think of it as an implication. So what are these operations? The end operation, of course, so the limit, if you have two objects, the limit is something that maps to both of them. The co-limit is something that both of them map into. So you can see immediately here that the limit, if you have two words, x1 and x2, then their limit is basically the minimum of these two functions. And that lives precisely on all the text that contain both x1 and x2. And that's kind of an end operator. And the OR operator is the co-limit, which lives on things that contain either x1 or x2. And when I say, and this is the OR operator, and so together these two things, they make, of course, a lattice. But moreover, you have an extra piece of information here, which is the implication. So what happens is that the category, the monoidal category, which is the Boolean algebra, also has, it's not just monoidal, but it's complete. It's closed, I'm sorry, closed, which means that you can define this inner home. How does this inner home work? So this inner home, is you're supposed to think of this as implication. Okay, so we have here two texts, y and x. So we have this new function. Remember, bx and by are functions. Bx lives on the ideal of all things containing x. By lives on the ideal of all things containing y. So now this is a new function. And when you evaluate it, this is the home of the category on bc and by, the limit. So what does that actually mean? If by and bx evaluated on c is 1, you can work out what this means. It means that y implies x under the context c. So it means that, in this case, what imply means that any text that contains y and c will also contain x. Like, for example, okay, you may want to take y to be red and x to be blue. I mean, in general, red will not imply blue. But if you add something else, some other information like French flag, then you may expect that anything that contains red and French flag will probably contain also blue. Now, this is a very kind of rudimentary setup, but already shows us this basic structure. And the basic structure is what's called a Heyting algebra. Hailing algebra is a little bit more general than a Boolean algebra. Boolean algebra, we all know, it has basically and, or, and the negation operator. And the negation operator you can use to construct the implication. Okay, so this is the definition of a lattice, and when you have this negation operator, the implication basically is constructed by using this negation operator. But in our structure, which is a little bit more general, because it's also called a pseudo-Boolean structure, you don't have a negation operator. So in language, you don't necessarily expect that you would have a negation operator, but you still have an implication operator relative to context. So something implies something else, always relative to some context. And the implication sheaf is precisely the one that, evaluated on the context, will tell you if one implies the other. So that's the basic structure. But now, of course, you know, what these transformers learn, they don't learn just if it's something is, you know, if something is containing something else. They give a probability for that, because that's what they learn, actually. They learn the distribution probability that you can extend, for example, in text to by another word. So we want to enrich our structure. Instead of just using the Boolean algebra with just two elements, 0 and 1, use the interval, 0, 1. So we're going to interpret this as probabilities. Okay. So again, we're going to have a category which objects are texts. And now the morphism from one text to the other is going to be a number between 0 and 1. It's going to be the conditional probability extending from one to the other. Okay. So now what's the point here? The point, of course, is that conditional probabilities multiply. So if x1 is contained in x2 and x2 in x3, then you could say that the conditional probability of x1 be contained in x3 is the product of the other two. So that's precisely composition in this category. So we have a category, and this category is an enriched category over the monoidal category 0, 1. And you can. This is actually a subject which is well studied. And in general, what you expect for the morphism satisfies an inequality, this kind of inequality. We have equality, but not in all cases, because we'll see in the pre-sheaves we don't have necessarily an inequality. And this is just a slide to show that this is precisely a generalization of the previous situation. In other words, the Boolean algebra lives inside this interval category. And when we restrict ourselves just to the numbers 0 and 1, we recapture the previous situation. So now again, we want to write to construct this completion. So remember, we have this Yoneda embedding. And the idea of the Yoneda embedding is actually quite nice. So the idea of the Yoneda embedding is that, you know, if you have a category, if you want to know an object, it's equivalent to knowing the object is equivalent to knowing all the morphisms from that object to all the other objects, which is kind of something which is a very, you know, nice idea. That basically, because also when you have text, if you think you're a computer and so on, all you see is just a bunch of symbols, right? You have like absolutely no other information about what you're getting. The only other information you're getting is this particular text is included in some other texts, right? So these are all the morphisms. So how can you get a structure just by looking at the morphisms? And so the idea of the Yoneda embedding, which is a basic feature of category theory, is that you know an object by looking at all the morphisms from that object to all other objects, or from other objects to that object. And when we say these morphisms, you set it up basically as functors. You take all functors with values in whatever category the morphisms are taking values in. So in usual category theory, there would be values in sets. Here, of course, we're using 0, 1. So if one works now, what are these so-called pre-sheaves? So this category of pre-sheaves, you can see that actually the condition that we need to have is that the morphism between x and y is less than or equal to the morphism between f of x and f of y. So f of x, f is just a map from L into 0, 1. Just like before we had bx and by. Bx was only taking values in 0 and 1, and it was only telling us if one text is included in another. It's either 100% included or, you know, not included at all. And here we have this probability structure. And so keep in mind this condition here, because, you know, for us now, we're just doing probability theory, and we're not really sure what that means. But in a few moments, we're going to be doing metric spaces, and it will be related to the metric inequality in that case, to the triangle inequality. So basically, you take this category of functions now, and you construct this new category of presheaves, or co-presheaves would be the more correct name. And your original category is embedded in there. So there's a fully faithful embedding of the original category L into this new category. But this new category now has more stuff. This new category has, as we said, has limits and co-limits. And these limits and co-limits, they also provide you with a Heyting algebra. So you know, one has to work out, so by general theory, you can work out what is the morphism between presheaves, and you find out that you have to take the minimum overall, point-wise minimum of the inner home here. I mean, so so 0, 1 itself is a category over 0, 1. Okay, that's why this works, because both L and 0, 1 are categories over 0, 1. And let me just go back a few slides to show you. Oh, sorry, I'm going the other way. Okay. Yeah, so here I just kind of passed this very quickly. But you know, when you have two numbers inside the interval 0, 1, what is the home you associate to them? The home is the minimum of 1 over t over s. And then if you do that, then you can show that the interval 0, 1 is a category over itself. Okay. Because it satisfies inequality that we said this categories over 0, 1 must satisfy. So, okay, so we can define this completion. And so what I would like to think is that, so, you know, there's many places in mathematics where this kind of completions give a duality between syntax and semantics. Okay, these are called presheaves. For example, let me give you another example. Okay, in algebra, it's well known. In commutative algebra, it's well known that there is a duality between spaces and algebras of functions on the spaces. So you have the spaces and the coordinates on the space, okay, which you can multiply, and they form an algebra. And you can go from, there's a construction called the spec of a ring. The spec of a ring is basically you take the set of all prime ideals. So just like we have here ideals, there you also take ideals. And when you take the space, the space of its ideals, you construct a space. So for example, if I take polynomials in two variables, x and y, the corresponding space would be C2. Well, I'm thinking about complex variables. So in that case, the ideal, if you have an algebra, the notion of an ideal is something that you can act on the algebra, and then you remain in the same space. It's kind of a fixed space for a space you can act on with the algebra. So, but different coordinate algebras can correspond to the same space, right? I mean, you can change, you have one space, one underlying space, and different coordinate algebras. So ideally, if you want to think of this mathematically, you would want to say something like, and when I first started thinking about language, I thought, okay, we can think of language as an algebra, and then, you know, we can construct some sort of space, underlying space, and then the translation between the two languages is going to be a change of coordinates, basically. Now, of course, language, if you think of language as an algebra, you have to think of it as a non-commutative algebra, because when you take two pieces of text and you put them together, it matters what the order is. And so, you know, one has to ask themselves, what is the corresponding relation, what's the corresponding construction for non-commutative algebras? And there is one, and the generalization of an ideal, in that case, is a module. So you can take all representations of the algebra, and this forms a category. Now, to get back to the discussion that we're having here, a module in that case is precisely a sheaf. So this idea of taking sheaves and considering them as the semantic space for a syntactic structure, and the syntactic structure would be, for example, the original category, which is enriched over 0, 1, the category of texts, and the category of sheaves is this category of functions with all this extra structure. So that's a kind of like very basic thing in mathematics, going from algebra to geometry. And again, so this space is much richer, the space of functions. You can consider the limits and co-limits, which is the minimum and maximum of the two functions. And the limit is going to be supported on texts that contain both x and y, and the co-limit on texts that contain either x or y. Okay, and so actually this operator here, it's very much like what happens in Latin semantic analysis when you take, all the matrix of co-appearances of texts. You have, you have a bunch of documents, you have a bunch of terms, and then you construct a co-appearance matrix of the words. So that's kind of like exactly what this AND operation is. And you also have, of course, the implication operator, which will say under what conditions y will imply x. So you evaluate it on some condition c. This means it's a kind of probabilistic version of the previous story where I had blue implies red under the condition of French flag. So in this case, there's so basically for those of you that know a little bit more about category theory, the inner home is adjoint to the limit end. Okay, so you can basically, so here we're using the Yoneda lemma. By the Yoneda lemma, whatever this thing is, this pre-sheaf evaluated on that is equal to L hat of this. And then by the defining property of the inner home, we must have that it's equal to that. And so we can compute it, and we get some sort of probabilistic version of implication. By the way, for those of you who may have heard the name, I mean, so this category, this sort of approach, it also kind of touches something called a topos. So a topos is a category of sheaves, which is where the morphisms actually take values in sets. So we don't have, so they have sets, we have 0, 1. But in case you're surprised why we would get a Heyting algebra, which is something that comes from logic, why on earth would it appear here? I mean, in topos theory, actually, this is completely natural. And topos is the kind of the categories that combine geometry, algebra, and logic. So from that point of view, one may expect that. Okay, so then next I want to move on to some more geometric picture. So for the moment, we have these probabilities, this probabilistic picture. But when you have 0, 1 with multiplication, if you apply minus log, you can go to 0 infinity with addition. So 0 infinity is also a monoidal category. It has this addition gives the monoidal structure with inner home. And of course, it changes the order, right? So if s is less than or equal to t, then minus log t is less than or equal to minus log s. But what we do is we define now a new category, which is just gotten from the previous one with the same objects, but just apply minus log to the morphisms that had previously. So I take minus log of the probability. Now, the interesting thing is, before here we had the condition for the morphisms was that L of xy times L of yz is less than or equal to L of xz. Well, now if I apply minus logs, what do I get? I get something with additions, and I get this precise statement, which of course is the triangle inequality. So basically this is telling you that actually we have a metric space. Now, what kind of metric is this? This metric is non-symmetric. So the distance between x and y is different than the distance between y and x. Okay? When I first saw that, I thought something was wrong. But actually, it turns out that that's perfectly natural, normal, and so on. And people that are doing measure theory, metric spaces, they've been talking about this stuff all the time. And it's kind of like, they give always the idea that, if you want to go up a hill, it's different to go up. You have to expend some energy, but to come down, you don't. So this shows up everywhere in applications. So this space M is a generalized metric space in this sense. And of course, then you can have all the same. So, just like before, now we're trying to construct the pre-sheaves. So we notice that R plus is itself a metric space. So what's the metric on R plus? The metric is the maximum. So the distance between S and T is the maximum of 0 and T minus S. Okay, so if you use that metric and you take isometries between M and this space 0 infinity with that metric, you get this space of presheaves, which is a metric space in which the original metric space has been isometrically embedded. So the Yoneda lemma in this case boils down to the fact that this Yoneda embedding gives you an isometry in this bigger space. And what are the presheaves? What is the condition for the presheaves? The condition for the presheaves is that the distance between phi x and phi y is less than the original distance between x and y. So these actually are contractions. So it's a very natural class. In fact, actually, Levier, is there a question? Sorry. Oh, sorry. Levier studied those back in the 70s, and in fact related them to logic. And there are other places where they're studied. So these are basically just the contractions, or if you want, they're kind of called Lipschitz maps, with Lipschitz constant equal to 1. So then this M hat becomes also a category over 0 infinity, which is a generalized metric space. The distance basically is just the supremum distance, the sup. The supremum between these two functions gives you the distance. And of course, you can have, again, limits, colimits, and inner Hom that form a Heyting lattice, a Heyting algebra. All right. And then lastly, let me just say a couple of things about another interpretation. This is not just a metric space. This structure of end, it turns out to define what's called a tropical module. So if you've heard about the max plus algebra, basically what it means is you take two numbers, instead of the addition, you replace by maximum. So take 2 and 3, and the addition is not 5, but it's 3. And now when you multiply two things, you add them. So you take 2 times 3, it's not 6, but it's 5. So that's kind of basically taking logarithms. It's a logarithmic. It's actually taking logarithms, and you may ask, okay, well, you may say, well, of course, if you want to take multiplication to addition, you use logarithm, but what about this crazy maximum thing? Well, actually, this, basically what it means is a way of taking logarithm and sending the base of logarithm to infinity. Yeah, and it's actually, it's a long-studied story. By the way, it's called tropical because one of the guys that was the main proponents of this theory was working in Brazil. So there's no underlying, mystical reason for tropical and so on. But as you can see, this maximum comes from the following identity: that if you take numbers a and number b, exponentiate them, divide by this parameter h bar, take h log, and then send h to 0, that is the maximum. Okay, so that's how you can transfer. There's a whole subject of tropical geometry and using optimization theory and in many places. And what we find here is that actually this completion, M hat, is actually is a tropical module. So first remember that these maps, these presheaves are supposed to be contractions. So in particular, I can just shift them by a constant amount. They just remain contractions. So if I have lambda 1 plus phi and lambda 2 plus psi, this is precisely equal, is the maximum of this thing, and the maximum is precisely the tropical sum of these two products. So that makes this a tropical space, and you can study it as a tropical space. There's a lot of things known, and actually, let me just say just one more word about this. So this gives you a way to get equations. So maybe you're familiar about sort of kind of crazy equations coming out of neural networks that learn to continue things, and you get things like the vector for king minus the vector for queen is equal to the vector for man minus the vector for woman. I don't know if you've seen this kind of stuff. That was sort of originally discovered by Mikolov and company. And but nobody knows why you get this kind of things. Well, here we get something similar actually. So if you have x1 a text included in y, then you can show that this equation holds. And this is in L hat. So this is in the 0, 1 case. And then there's another one. So basically the idea is that, you know, this thing is supposed to live on things that contain both x1 and y, but the value it takes is not that of y, it's the value of x1. So you have to multiply by this probability to get the right value. So you get this kind of relation. So applying, of course, minus log to all that, you get this kind of equations. And so you get two equations, okay, for this, so this phi x1, in practice, you can think of it in the following way. You can say that this is basically the distance. I mean, this is the function that gives you the distance of any other text from this text. And you get the system, and you can get this particular equation. But you can now understand that, you know, the transformer, what it's actually doing is solving this huge tropical linear system of equations. That's another way of thinking about it. OK, so now I want to go into quantum stuff. So the idea is, like, can we get a quantum state that learns the continuations? OK, so playing around with this, we just realized that, yes, you can. And it's actually quite simple, theoretically, of course, how to do that. You just take a sum of all texts. Now we're thinking about, so we shift gears now, and we go into quantum space, where we have a vector space generated by words. And so therefore, if I have, for example, let me give a simple example, text with 2 words, they will be in V tensor V. So I consider this state psi, which gives me exactly the, by the Born rule, gives me the right probability of this sentence appearing. Okay. So from this, then, I can get the projection operator. You can just compute the projection operator and trace out the first part. So let's say we trace out the x component here. Okay, so we get some density, of course, because we started with the density. And the interesting thing about this is that if you use this operator to map then different words, words that have the same continuation will have the same vector. Okay, so it kind of learns to classify things relative to their continuations. So this is why I'm talking about this in relation to the previous one. And actually, the vector you get, in fact, turns out that it has a kind of like meaning in things that some people, not me, but I mean, when I found this out, I didn't know about this Bhattacharya coefficient that I'm going to show you right now. So basically, this kind of considers a text as defining a conditional probability on all the other texts that can go with it. Okay, so so basically these coefficients here that you see turn out to be something called the Bhattacharya coefficient, which is something that you use to compare the overlap between distributions. Okay, and then if you take square root of 1 minus that, then you get something called the Hellinger distance, and this satisfies the metric inequalities. Okay, so for example, you know, if I take some corpus like big mountain, tall mountain, cold night, and chilly night, and I perform this procedure where I take the projection of psi and I trace out the first part, I trace out the second part here, then the image of big and tall will be the same, and the image of cold and chilly will be the same. You can, you know, this is a very simple calculation. So it learns to classify things according to their continuations. Okay, so the general case, of course, if you have something like that. So now we want to use graphical notation to make more sense out of it. So where am I going here? I want to get a functor from what I was talking about previously to something quantum. Okay, and the way to do that is, well, let's consider the state psi, which is the normalized sum of all the texts. And yeah, everybody loves here this as a spider. So you know, this is the vector psi, and this is the projection on it. So what we can do is we can fix some of these things and let the last one open. This will be precisely this map that will give you the probability of something being after this expression. So let me see here. Yeah, so I define this trace. When I compose these two things, it means I trace out. That's a tracing out. I fix this to be xi1, and I leave this open. That's an operator from V to V. It's precisely the operator that gives me the probability of continuation from x1, from xi1 to any other word. Okay, so this is a positive operator, and I call it hat, and if it's normalized, I divide by the trace, which is the probability of xi1, and normalize it. And actually, what's interesting is that, well, I mean, so basically you can see that you can write a relation. So rho hat of xi1 is the sum of all rho hats of xi2, xi1, all things that contain it. And actually, when you normalize, you get this sum, but with the conditional probabilities. So to finish, let me show you what the functor is. You just take basically this functor that to every expression you associate this corresponding density operator. Okay, and this density operator is because of this equation that I showed you before. It shows you precisely that this rho hat x2, x1 is less than or equal. In what sense? In the sense that if you take positive operators, they define a cone, and a cone in a vector space defines a partial ordering, and this is, this is bigger than that if rho xi1 minus rho xi2, xi1 is in the cone. So in that sense, it defines is a partial order. So this is a posted map, and then if you decorate this with the corresponding probabilities, you get from the 0-1 category a functor. And last thing, I want to say something about this crazy state psi, which is actually quite simple in the sense you just take the sum of all possible texts and you normalize it. How on earth could you compute it? Of course, the only way I know putatively to compute it would be to approximate it with some isometric tensor network. And with tensor networks, of course, isometric means there are isometries here. So these are quantum gates. So actually, this is exactly a quantum circuit. And you can use different, these are different ansatz, right? So this is like a binary tree ansatz, this is an MPS ansatz, and there's other ones. And you can just approximate psi with one of these things and try to play the game. Okay, so I'm going to stop here. I can hear you, yeah.
Okay. Thanks a lot for your talk. So regarding the first part of your talk, have you thought about whether an interpretation for this Uneda embedding, when applied to the meaning of words, could be like kind of a duality, like how you can understand the meaning of a word? You can understand it as its extension, which means the set of, maybe you would say, context where it applies or where it is true, or as its intention with an S, which means something like what it intrinsically is, or like, in my understanding, what like the entry in the dictionary. Like
I see.
It would give a finite description of what that word is, independently of what the context where it's applied. Could you interpret this?
Sorry, would you mind summarizing the question as well?
Sure, yeah. So the question is that, we're trying to sort of classify words according to their extensions. And you're asking if we can use some sort of other internal classification, for example, by a dictionary or some other property, as an intention, if I said it correctly. I don't know if, but what I can say, let me see if it's relevant. Well, certainly I can say one thing, which is, of course, you can go into texts which contain the particular text, or you can go to the contained text. You can go bigger or smaller. And that's very much related to, I mean, of course, there's two ways to complete, right? You take the filters or the ideals. You take the bigger things or the smaller things. And there's a duality between them. And there's something called the Isbell correspondence. And then you can get this, you get an adjunction, and then you get the fixed part of this adjunction corresponds to the concepts. But you were saying something else. You were saying something about some sort of intent, but how do you find this intent? Okay, all right.
Thank you.
Sorry.
Well, isn't the Uneda embedding a reconstruction theorem? In which case, can't we just find a way to reconstruct the definition from all these?
Yeah.
And you mind repeating it?
Yeah. So the question is isn't the Uneda lemma a reconstruction theorem? in which case you would be able to reconstruct. Yeah, you can reconstruct, but in what sense, though? You can reconstruct it in the sense that, you know, if you know all the morphisms, which are all the text extensions. So I'm only putting in my model the bare minimum, which is just the pure text. I'm trying to like avoid putting any other thing, you know. Of course, the human brain puts a lot of other stuff because we have like all the senses. So we have other things annotated. So I mean, you know, I mean, this guy here, this poor guy, is only going to know an apple by the sentences, right? I mean, we can eat it, we can smell it, and so on. So these will be other features of it, and certainly will be added, but you know, obviously, it has to be added later. Yeah.
So, as you know, this approach is dear to me.
Yeah.
But I'm worrying about, so you're modeling text as a monoid, and then ordering
As a
monoid.
Oh, monoid was kind of parenthetical, but mostly as a poset.
Right. But
I can tell you how to.
if we take a piece of text
Yeah.
and treat another piece of text, we will still get text.
Yeah, I can say something about that. This is a footnote. Yeah. So he was saying that we can model text as a language as a monoid. In other words, we can put two texts together.
That was just the first.
Yeah. Okay. Sorry. Please continue. Yeah. Sure. Sorry.
Yeah. I mean, the ordering is not closed under appending more text. If you say I'm ordering texts by simply inclusion, if one piece of text can be included in the middle of another piece of text, then if I add a word to each of these two pieces of text, the inclusion will not be preserved.
Yeah. No, it will not be.
If I begin the sentence with however, and I had two sentences,
Sure.
one of which was included in the other one after however.
Of course not. It will not be. Yeah. Of course not. Yeah.
Moreover, you know, if I say I love you very much, if I say I love you very, very, very much, it's a different sentence. Then if I say 35 times that I love you very
Sure.
much, and if I say 36 times,
Yeah.
that will be indistinguishable, whereas 5 and 6 will be distinguishable, and
No.
1 and 2 will be distinguishable. So the approach with ordering and concatenation is needy.
Well, actually, okay. Okay, so can I repeat? Yeah. So basically the idea, the question was, the observation is that, you know, when you have a text in the middle of another one, then you can add a word to the middle text and get a new sentence, basically, that will not be, I mean, it's a complete new relation in my framework. But so I can tell you, because I thought about that, you know, how does the monoid picture compare to this picture? Well, actually, there's a very, very direct relation. So if you start with a monoid, which means that, you know, it's a category with one object, and every text defines a morphism from that object to itself. How do you get this one? Well, what you have to do is you have to consider the twisted arrow category. So you take the category of arrows, and this is a classical construction in category theory. You take the category of arrows. Sir?
Most people will know here what's the twisted arrow category.
We know. Yeah. I mean, what it is very simple, actually. You start with a category, and then you construct a new category by considering the arrows of the original category as objects. Okay. And what are morphisms? Well, if you have two arrows, you say you have a morphism if you can factor one object in a way that contains the other. It's also called the factorization category. So that means basically you can multiply on the left and on the right. And so the monoid picture is actually, I mean, from the monoid picture you can go to this picture, and you know, I haven't thought about the other way around. I haven't thought about it very specifically, but you know, I probably think they're equivalent. That's what I think. Yeah.
Thank you. Yeah, I think we'll have to
okay.
more discussions
Okay.
After the session. Let's
Okay.
thank our speaker again.
Thank you. All right. You're up. Yes. This is your. Thank you. Oh. This is mine.
Okay, so yep, this is the last talk of the day. It's been a long day, so let's make it quick. So here's a little demo of DiscoPy. So the name stands. Oh yeah. Okay, sorry. Up, 720. Okay, I think now we can start. Oh, it's much bigger now. Okay. Good. So yeah, DiscoPy. The name stands for Distributional Compositional Python. So you just take DiscoCat and replace the cat by Python. So it started as an implementation of DiscoCat, and it turned into more generally a toolbox for quantum computing, for computational linguistics, and for applied category theory. So let's have a brief outline for this talk. First, I'll talk about diagrams. Diagrams as a data structure for quantum and for linguistics. And then functors as a way to do high level and high performance computing. And finally, a few words on diagrammatic differentiation and its application to QNLP. So the references that this talk is based on, first the DiscoPy paper that we submitted to Applied Category Theory 2 years ago with Giovanni and Bob. Then a little abstract that we submitted to QPL just this year with joint work with Richie and Giovanni again. And also my PhD thesis, which I defended last Friday, and which will, thank you. And which will appear sometime soon once I have done the corrections. So let's get on with the talk. A little bit of maths just to warm up. So a monoidal signature is a tuple. It's got a set of wires, sigma 0, a set of boxes, sigma 1, and then it's got these two functions that map every box to the list of input wires and output wires. So here the little star will be the Kleene star, so the free monoid, the lists of wires. Now a triple, a layer is given by a triple. It's got some objects on the left, a box in the middle, and some objects on the right. So let's look at what DiscoPy, how DiscoPy implements layers. Well, you can implement tie will be the sigma 0 in our case, so the types for the wires. Box will be sigma 1, and ID is just some bureaucracy that we need to keep the types in check. So you start with some types, X, Y, Z, W. A box, F, will have some domain, Y, and some codomain, W, so the input and output wires. And then you put it next to an X on the left and a Z on the right, and you get a little layer. So you can draw this layer, but you can also store it as a piece of Python. So what can you do with layers? Well, you can compose them in sequence, and you get diagrams. So a diagram will be given by a domain, and then a list of composable layers. So just give me D1 up to Dn. Each is a layer, and each composes with the previous. So the domain of Di plus 1 is the codomain of Di, and also it type checks with the domain of the diagram overall. So for example, the identity diagram has no boxes in it, so it's just got a domain, and it has no layers at all. So that would be the empty list. Now, once you have diagrams, you can compose them in sequence, just concatenate the lists, and you can compose them in parallel, which means that essentially you do first the left guy with some wires on the right, then you do the right guy with some wires on the left. So sequence, composing in sequence is this double chevron here, and composing in parallel will be this little @ symbol. That's the closest we could find in Python. So let's draw a little diagram. We'll need more boxes if we want it to be interesting. So let's have some G, H, E. They all have domains and codomains. If you don't want a codomain, well, you can always have this tie open close bracket will just be the empty list of wires. And now let's compose some things together. So G, then the layer that we've just defined before, then E next to H, and you can draw the thing, and it looks like this. So we have our box G first. It's got three wires out. Then you do F in the middle. Then you do E on the side, and H. Well, you get a diagram. And I guess the point is you can draw this diagram, but more importantly, you can store it as a piece of Python. So,
so if on the third one, you also have a G on the left in the same layer with E.
yep.
They want you to slide M down and E up and keep
Well, that's good. So sometimes two diagrams will represent the same process as Dushko just mentioned. And DiscoPy allows you to do diagram rewriting so that you can first check if two diagrams are equal up to your notion of equality. Or you can also use it to find an optimal diagram for a given process. So as you just noticed, well, these two diagrams will be equal in the sense that here the box E and F are independent. There are no wires in between them. So it doesn't matter whether I first do E on the left and then F on the right, or vice versa. And that's called the interchanger. So here I have my diagram that I've defined before. I have the normal form of the diagram on the right. And if you call diagram.normal form, you will get the guy on the right. So that's a way of checking if two diagrams represent the same process. You can also use it to do optimization. So now we can add more kinds of boxes. So we can add special boxes for swapping two wires. We can add boxes for cups and caps that we've seen a lot today, for spiders. Basically, any kind of diagram that you can find in Bob's book, you can draw it in Python now. So, well, one application for these diagrams is linguistics. So the idea is you can represent any kind of grammatical framework in terms of diagrams. So here's a little example with a context-free grammar. You've got a bunch of vocabulary, Alice loves Bob, a bunch of non-terminals, S, N, transitive verb, intransitive verb, and then you've got a bunch of rewrite rules. So that would be a context-free grammar. You have the rule that tells you that Alice is a noun, the rule that tells you that if you have a transitive verb next to a noun, you get an intransitive verb phrase. If you have a noun next to an intransitive verb phrase, you get a sentence. So that's a little grammar. And a grammatical derivation in this grammar will correspond to a diagram. So here our diagram will be a tree because we have a context-free grammar. Yep, go ahead.
Can I ask two things about this?
Mm-hmm.
One is that one item in your vocabulary is a declined verb. What's the rule? Do you only include infinitives, or do you include plurals of nouns?
Well, I don't encode anything. I guess the linguists would encode stuff. And I guess that's a matter of linguistics in the sense that you will define a grammar, and your grammar will depend on the language you're trying to describe, but will also depend on the level of precision you want in your grammatical model. So I guess here the idea is you have all the freedom you want. You can come up with any kind of rule. Here I just picked sort of a stupid example, or the simplest example I could pick. But if you wanted more complicated examples, you could. Here, basically the example is a context-free grammar. So by definition, a context-free grammar has a vocabulary, a set of non-terminals, and a set of rewrite rules. And it also has this property that the rewrite rules always have exactly one guy on the right-hand side or left-hand side, depending on your convention. So essentially, any context-free grammar gives you a bunch of these rules. The rules, they are boxes in DiscoPy. So now, if you have a bunch of these boxes, a bunch of these rules, you can compose them. And here it happens to be composed in the shape of a tree. So this tree would have the sentence type as a root and the terminals as the leaves. And now this diagram you can think of as a proof that Alice loves Bob is a grammatical sentence in this particular grammar. So if you come up with more complicated grammars, you can describe more complicated languages. So I guess if you had a context-sensitive grammar, for example, now your rules would take context into account in the sense that you wouldn't have this property of only one output to each rule. But that's a little example of a context-free grammar. We can play the same game with pre-group grammars, which are the ones that Bob has been using a lot. So I guess that was the sort of the minimum we wanted to do with DiscoPy was to draw these pre-group diagrams. And here's what it looks like. You have a sentence type and a noun type. Now you have some nouns, Alice and Bob, a verb, loves, that has this complex type like the right adjoint of N on the left, the left adjoint of N on the right, and the sentence in the middle. And basically what that tells you is you can take Alice loves Bob, cancel the N with its adjoint, and similarly on the other side you get a grammatical derivation, and this diagram is a proof that Alice loves Bob is grammatical in your pre-group. Yep.
Can I ask again?
Sure.
One thing I never understood about this. So take a verb that can be both transitive and intransitive.
Oh, right, yeah. So I guess in the context-free grammar case, what this would look like is you would have rules. Here you have the rule Alice goes to N, but maybe Alice could be a verb, I don't know, it could be any other thing if you invent your own language. And you would have potentially many rules that correspond to the same word. So for example, the word type is both a noun but also a verb. And in this particular framework, you would model this as by saying that I have two rules, a rule that takes type to noun, a rule that takes type to verb. And so that's how you would model lexical ambiguity, in the sense that if a word has several types, it comes with several rules that sends that word to the different types. And in the pre-group case, the way you would say this is that you define a pre-group as a bunch of dictionary entries, and the same word could have many dictionary entries. So if type is a noun, it has a dictionary entry for that. If it's a verb, it has another dictionary entry. And those would correspond to different boxes in Discopi. So I guess that's the main takeaway here. Word is just a kind of box, which was sort of suited for pre-groups, but it's just like any other box. And if you give me a collection of boxes, essentially what you've defined is a grammar. So, well, I guess you also need to tell me what your sentence type is. But all right. So that's a pre-group grammar. You can do context-free grammar. You can do any formal grammar like context-sensitive or even unrestricted grammar if you like. We've worked with dependency grammars. And I guess, yeah, modeling more grammatical frameworks is future work. So you can use diagrams for grammar, for formal linguistics. You can use diagrams for quantum computing. So any kind of quantum process you can draw as a diagram. And so here's a little example with a circuit. Well, from discopi.quantum, you import the control knot, you import the Hadamard, the X rotation, the ket, and square root even if you want some scalars around. And you can compose those together to make a circuit. So here we have a ket with 0, 0, followed by an H on one qubit and a X rotation on the other. Then we do a control knot, and ta-da, you get a diagram. So that's the diagram for a circuit. You can also draw diagrams for the ZX calculus that Bob came up with and Ross. So you take your circuit and you can replace the gates. So this controlled NOT gate, for example, you replace it by a green and a red spider. And now you can map your circuit to the ZX calculus using Discopi. You have this circuit to ZX method. And you can also use Discopi to call other dedicated libraries for rewriting diagrams in the ZX calculus. So for example, if you took this diagram here, it's got some complicated stuff like a Hadamard gate, but if you simplify it, you get a very simple diagram on the right. So that's sort of the main feature of Discopi is it allows you to draw any kind of diagram and then to map from one kind of diagram to another, and potentially use these diagrams as a high-level way to represent computation, so that here you can rewrite your ZX diagram and it would correspond to optimizing your quantum circuit. That's the general idea. And we keep on adding more tools to the toolbox. So on the quantum side of things, we've been implementing classical quantum processes. So basically all of Bob's Dodo book now is implemented in Python. So if you take any piece of his book, you write down the diagram in DiscoPy, and you can start playing around with any classical quantum process. So essentially, that means you need extra kinds of wires for the classical wires, and that way you get more processes that you can talk about. You can do, so from qubits, which is the example I'm showing here, you can go to arbitrary dimensional qubits, which are, for now, not very useful because the quantum computers we have access to right now don't use anything else than qubits, but well, people work with qtrits or whatever, so you can implement them in DiscoPy. We've been working on symbolic circuits, so circuits come with parameters, like the x rotation here is parameterized by a phase, where you can put a symbolic parameter inside. So we'll get to see a little example of that at the end of the talk. And we've been doing more work on a different paradigm for quantum computing, where instead of qubits and gates, you have quantum linear optical computing. So you have photons, and you have interferometers between them, and you can do quantum computing with this. And that's still work in progress based on some theoretical work by Giovanni and Bob. So we're implementing that. And now, OK, we have diagrams. Diagrams are very general. They can represent cooking recipes. They can represent grammatical reductions. They can represent quantum processes. What do we do with these diagrams? Well, functors take a diagram and interpret them. So what is a functor? It's got an object mapping. It sends types to types. An arrow mapping. It sends boxes to diagrams. So one example would be circuit to ZX, as we've just seen before. Another example would be qubit to photonics. That's what we're working on. And the main example, I guess, the topic of this conference is QNLP models. And these QNLP models are functors as well. So you take your grammatical sentence for Alice loves Bob, and you send the verb loves to some ansatz. You send Alice to ket 0 and Bob to ket 1. You apply the functor, and you get a little circuit. So this was basically copied and pasted from 3 years ago, the first QNLP conference. And basically, that's what DiscoPy was implemented for, to run these QNLP experiments. Now, we have different ways of evaluating these functors. We can execute them on quantum devices using the ticket compiler. We can also do high-performance classical simulation using JAX or PyTorch, TensorFlow, TensorNet, any kind of backend you want for evaluating diagrams in terms of matrices. So last bit of the talk, well, we have functors for QNLP. They come with parameters, and we'd like to find the optimal parameters in some task. And, well, we need gradients. So, well, with Richie and Giovanni, came up with this diagrammatic differentiation where you can differentiate any diagram, and it obeys very simple rules like the product rule for composition and for tensor. And you can differentiate ZX diagrams, so here's the differentiation for spider. And, well, you can also differentiate circuits that are evaluated as quantum processes by using the parameter shift rule that comes from this Schuld et al. Result. So essentially, you use the quantum computer to compute its own gradient by shifting some parameters. And here's what it looks like in ZX. You have some gate and its conjugate. You tensor them together. You take the gradient of this, and you can rewrite it as a sum of, or a difference of the same diagram shifted by some pi/2 phase. Some note, we don't need to care. OK, how does it look like in DiscoPy? Well, first you import some symbol from SymPy. You put it as the phase of your, as the parameter of your circuit. And now you just need to do circuit.grad, and you get a sum of circuits that evaluate to the gradient of the original one. And basically, you can use this to find the optimal functor in your QNLP task based on some data. So that's it. What's left as future work? Well, we want to do more linguistics. So, for example, Manouche talked about anaphora and ellipsis earlier today using Fock spaces. We want to implement more of this in DiscoPy. We want to do more quantum stuff. So photonics also happens to be about Fock spaces, and that's work in progress. and more applied category theory in general. So there's been work on using DiscoPy to do cognitive science, and well, I hope there will be more. So please get in touch and contribute to DiscoPy. It's open source, and we're always looking for more contributors. Thanks. Yep. Wait, what do you mean pushing layer?
When you did what you, for instance, showed.
Oh yeah, the interchanger.
Right.
Yeah.
So how is that implemented? Can I tell it slide E from this layer to layer?
Yeah, that's it. So basically, if you want to implement this interchanger, you have a diagram you want to rewrite. It's got this ordering in the boxes. So technically, it's a pre-monoidal diagram if you want. And then you can apply an interchanger by just specifying the box at level I goes to the box at level j, and it will either give you the new diagram or raise an axiom error if the wires were connected and you can't actually pass one box past another.
Not the question for the conference, but there, the obvious thing is the duality of layers and strings. You can use the same module to just put the layers upside down and they become strings. It is the so-called Fourier transform.
Oh, wow. Yeah. Well, I want to know more about this, but yep, that's a cool remark. Thanks.